introduce our semantics work on Verilog. And due to the time constraints, I won't delve into the details of Verilog and the semantics. So don't worry, you could easily understand my talk. I will firstly introduce what is Verilog, and then give a motivation example to explain why we need the Verilog semantics work at this point. Then I will give a brief introduction to Lambda V, the core language we present in this work. And finally, I will show you usefulness of Lambda V. Verilog is the most popular hardware description language which is used to define hardware. So let's compare it with software languages like C and Java. While C and Java programs can be compiled into executables, Verilog programs can be synthesized into circuit-like representation. Oops, sorry. Yeah. And yes, the Lambda V programs can be synthesized into circuit-like representation, which can be further manufactured into the real circuits, like the chips in your mobile phone or laptop. So when we develop software, we need to test them by running executables on various test cases. But such tests cannot be performed on the real circuit to test real circuits because producing real circuits can be very expensive. So instead, to ensure the correctness of hardware designs, we usually test Verilog programs by simulation, which is similar to interpreting like a Java program. Verilog is already a mature language, so why we need a semantics work at this point? Well, there are several reasons. Today, in the field of hardware design, we are witnessing a shift from general-purpose processor to domain-specific architectures, which is largely driven by the proliferation of AI techniques. And such a new trend raises new challenges in productivity, reliability, and security in hardware development. At the meantime, Verilog is an important infrastructure in hardware design. New languages like Chisel use Verilog as backend because Verilog has industrial strength support for simulation and synthesis. And also, many existing hardware security and reliability techniques are built for Verilog. However, Verilog is designed by hardware guys. They don't really know PL. So Verilog has a number of semantic pitfalls which confuse hardware developers and language tool developers, which further lead to bugs. Let's take a look at a simple example. So this is a Verilog program, and you don't need to understand every detail. I will explain the key parts. So Verilog uses modules to organize and reuse code. And then here, there are some data declarations, which is very similar to variable declarations in software language. So here, we define 4 variables. They are all 1-bit values. At the bottom, we want to connect variables A and B by an AND gate. In Verilog, there are 2 ways to do this, which are usually considered equivalent. The first way is to use continuous assignment. It's a unique feature of Verilog. So when we write a code like this, then whenever A or B's value changes, the A and B, this expression will be recomputed, and the result will be used to update C2. And the second way to do this is to use always block like this. So we write some expressions following keyword always. And these expressions can be seen as trigger events. For example, post edge A means that A's value changes from 0 to 1. And next edge A means that A's value changes from 1 to 0. And the same goes for B. So basically, we enumerate all possible value changes of A and B. So whenever these events are triggered, then A and B will be recomputed, and the result will be used to update C1. So since that these 2 ways, it seems that they are equivalent, right? So to confirm this, we write this test bench to check the equivalence of these two ways. So if C1 is equals to C2, then the program will display same. Otherwise, it displays different. And we run this program by Icarus Verilog, which is virtually the most comprehensive open source Verilog simulator. And its result is surprisingly different. So if I were a hardware developer, I will feel confused. And you might think, is this a bug in the simulator? Well, to answer this question, we need to check the Verilog standard. And however, according to the standard, for this program, both same and different are possible outputs. So if I were a language 2 developer, I will also feel very confused. And finally, we found that actually it is a semantic pitfall in Verilog, and it is not the only one. After careful study of the Verilog standard, we found and summarized a series of semantic pitfalls and summarized them explain them in this table. For example, this row explains the pitfall we just solved. So to clarify these pitfalls, we need a core language with formal semantics. So we introduce lambda v, which is a core language, and it can be distinguished from Verilog programs. Lambda v has some favorable features. And first, it offers tractability as a core language. And Verilog is a very complicated language. So we need to carefully design lambda v to keep it as simple as possible. So here I just showed its syntax, runtime states, and transition rules. So it is fairly simple compared to the Verilog. And second, lambda v provides so far the most complete Verilog semantics. And we have implemented a compiler and a simulator for lambda v, which contains 27,000 lines of code. And here is an example. So the left side is the Verilog program we just saw. And our compiler will distinguish such program into a lambda v representation like this. So let's have a quick look at their corresponding parts. And the two can be found in our artifacts. And finally, lambda v is well tested to demonstrate the totality and conformance. I will explain this later. And these good features of lambda v can enable us to do some useful things. For example, it helps us to detect 3 categories of semantic bugs in open source simulators, and expose 4 types of ambiguities in Verilog specification. Also, it can facilitate language 2 development, such as concurrent execution. And I will explain the 3 points. Lambda v is not the only one semantics work for Verilog, but it is the most complete one. We compare lambda v with other semantics works for Verilog, and here we summarize the results. So basically, each column represents a Verilog feature, or a category of Verilog features. And we use different circles to represent different levels of support for Verilog features. So we can see lambda v is much more complete than all other semantics works, including the state of art. So basically, lambda v can fully support almost all Verilog features, except these 2, LT and STF. But LT is rarely used, and STF is like a library functions in software, so it is unnecessary to model all of them. And to be useful, lambda v should have 2 important properties. Totality, it means that we can distribute all Verilog programs into lambda v. And conformance, it means that the distributed programs should generate the same results as the original one. And to thoroughly validate these 2 properties, we test lambda v using such strategies. So first, given a Verilog program, we distribute it to a lambda v program. Then we run simulation on both programs and then compare their results. We use two comprehensive test suites. The first one comes from Icarus at Verilog, which is the most popular open source Verilog simulator that I mentioned before. And it has more than 800 test cases covering various Verilog features, so as shown in this table. So each feature is counted once if a test case uses it. So it is a thorough test suite. And the second one comes from open source projects like OpenPitot and Altera. And these Verilog programs are non-trivial, ranging from 100 to 1,500 lines of code. For example, it includes an implementation of a RISC-V CPU. So what is the testing result? We found that LambdaV can pass almost all of these cases, except several ones. And some cases are incorrectly written by the developers. And other cases cannot pass LambdaV's stricter type checker, because Verilog allows implicit type conversions, and and LambdaV is designed to reject such cases because we found that they often lead to bugs. So overall, LambdaV demonstrates the totality and conformance to accommodate the various language features and real-world programs. I will use a case study to show the usefulness of LambdaV. And we ask an undergraduate student who knows something about concurrent execution but is totally not familiar with Verilog. But with LambdaV, it took him about 100 hours to implement a concurrent execution tool, which works well on a popular benchmark called ITC99. And this benchmark is widely used, and it consists of real-world programs. And the concurrent execution tool written by the undergraduate students exhibits decent results in terms of branch coverage and performance. So to conclude, the new trend in the hardware development raises new challenges in productivity, reliability, and security. So to tackle these challenges, in this work, we propose LambdaV, an operational semantics for Verilog, which is tractable and well-tested. It can help clarify the pitfalls in Verilog and facilitate building language tools for Verilog, such as concurrent execution tools. We expect that LambdaV to be useful for more potential applications. So ultimately, we hope that we can bring the successful principles and experience in the software community into hardware development. And if you are interested in the semantics, and please refer to our paper. Thank you.
Please step up to the microphone to ask a question.
Thanks for talk. I'm glad to see you have some user study that ask if an undergraduate student can use this software semantics to understand the hardware language. But on the other side, I heard from many hardware people that when you learn a hardware language, you shouldn't use software thinking because it's wrong. You should use hardware thinking so that you can really understand the real semantics of their language. So I'm wondering, is it possible that, or maybe you have ever considered that maybe you can ask some hardware people to read this kind of formal semantics, or maybe you can explain that to them in some more intuitive way so that they can agree that yes, this is consistent with what the so-called hardware thinking.
Well, we will definitely do this in the future, but indeed there are huge difference between the hardware language and software language. But I think in software language we have many successful experience, I think, which are definitely useful for building hardware. Especially the experience that we use to manage very huge software projects. And nowadays, the hardware also become more and more complicated. So maybe a powerful CPU, its implementation may contain many lines of Verilog code. So we think we can definitely help to improve their productivity.
Yeah, I agree, because nowadays they also use like software-defined hardware, for example. So I
Yeah.
believe this should be possible, but maybe we should investigate this problem further to, to really convince those hardware people that you can have some formal model to explain what their languages are actually doing. Thanks for your honors.
Yeah, thank you.
You mentioned you have a two feature you do not cover. Are you choose to cover in the future work, or you purposely leave them out in the semantics?
Well, let me see. Let me show these two.
I think it's FT and yeah.
Yeah, maybe not, because, but it depends. So LT is rarely used, and also it is not synthesizable. So this feature is not commonly used in Verilog, but it is.
What is the usual use case in this particular LT? How hardware people normally use them?
Usually you use this tool in an extension of Verilog called System Verilog.
Oh, I see. So you choose to ignore this. You choose to not cover feature in the System Verilog.
Yeah, currently not.
Okay, cool. Sorry, I'm from industry. I'm from ARM basically, but from what I heard, most hardware company they use System Verilog very consistently because it's more useful for engineer to use System Verilog. But potentially that is one of the feature people using. So that's why I'm asking the question.
Okay, I see. Thank you.
I have a quick question. So what kind of, so you have a mechanized semantics, right? So you actually tested it against all these tests. So how did you actually implement the semantics? And did you also think about like formalizing it in a way that you can do proofs and prove some properties about the semantics?
We do this by testing, because we think even we can formally prove some like properties, but if our implementation has some bugs or has some problem, we cannot say our tooling or our tool chain is useful.
All right, thank you very much.
Okay,
Thank you, speaker. Session about regular expression matching using bit vector automata.
Okay, hi everyone. My name is Konstantinos Mamouras, and I will be presenting our work, regular expression matching using bit vector automata. This is joint work with Alexei Leglonek and Linkun Kong. So classical regular expressions are built from concatenation, non-deterministic choice, and Kleene star. And we know from Thomson that a classical regular expression, or regex as we say, can be translated into an epsilon NFA whose size is linear in the size of the regex. This is all very nice, but real-world regular expressions need more constructs than just the classical ones, including bounded repetition, also called counting, look-around assertions, and back references. In this work, we specifically focus on bounded repetition, which is known to not increase expressiveness, but makes regular expressions much more succinct. In fact, it is known that the smallest DFA that recognizes the regex dot star a dot n needs 2 to the n states. And an implication of that is that the smallest NFA that recognizes the same language needs at least n states. This is not just a theoretical curiosity. Bounded repetition can cause substantial performance degradation in existing regex engines. So you might be wondering, why do we care about all this? Well, regexes, and in particular regexes with bounded repetition, are widely used for extracting information from unstructured data. And the key computational problem that is relevant here is called regex matching, which amounts to finding occurrences of regular patterns in data sets. There are 2 main techniques for regex matching. One is based on backtracking search, and the other is based on automata simulation. The advantages of backtracking is that it's easy to implement, and it's also very easy to integrate advanced features like look around and back references. The main disadvantage is that backtracking has worst case complexity that is exponential in the length of the input text. So this is pretty bad. In fact, it has a name. It's called catastrophic backtracking. Now, for the case of automata-based regex engines, DFAs or NFAs are used, and there is an interesting trade-off here. DFAs require much more memory, but they're a lot faster to execute. NFAs, on the other hand, are much more memory efficient, but they can be pretty slow. Because of this trade-off, modern automata-based regex engines typically use a hybrid algorithm that combines both NFAs and DFAs. Now, most existing regex engines unfold boundary repetition before they can construct NFAs or DFAs. Unfortunately, this unfolding gives rise to NFAs of exponential size and therefore DFAs of doubly exponential size in the size of the regex. This means that the memory requirements can blow up, but also the throughput of matching can plummet. So, because of these issues, we are led to consider the classical model of non-deterministic counter automata, or NCAs, which are a natural succinct representation of regular patterns with boundary repetition. In fact, NCAs have already been considered in prior work. So we have recent work with collaborators on the design of a hardware accelerator for regex matching, which is directly inspired from the NCA model. There is also a paper from 2020 on the software regex engine CA. Here is the NCA for the regex dot star, sigma 1, followed by the repetition of sigma 2, sigma 3, sigma 4 from m to n times. The states Q3, Q4, and Q5 form the one and only loop of this NCA, where Q2 is the entry state of the loop and Q4 is the exit state. There are two kinds of states in the automaton. Some states don't have a counter. We also call these pure states. And some states have counter named X, and we call these counting states. A transition between counting states is annotated with 3 labels. The first one is a predicate sigma over the alphabet. This is also known as a character class. The second label is a guard, which is a predicate over the counter X. And the last label, which I call an action, is essentially an assignment to X using the previous value of X. Now look at the highlighted portion. This essentially says that to enter the loop, we set the counter to X. To repeat the loop, we check that X is less than n, and then we increment X by 1. And to exit the loop, we check that the value of the counter X lies between m and n. NCA simulation requires maintaining a configuration, which is a set of tokens of the form Q, I, where Q is a state and I is a counter value. If we fix a state Q, the set of all tokens whose first component is Q can be represented with a bit vector of size n. Let's call this V, where V of I is equal to 1 if and only if the token Q, I belongs to the configuration of the automaton. This gives rise to the concept of a non-deterministic bit vector automaton, which associates a bit vector to each state. Note that the NBVA has exactly the same topology as the corresponding NCA. The difference is that it manipulates bit vectors instead of counters. States are classified according to the size of their bit vectors. Now, a transition from a state of type M to a state of type N is annotated with a character class sigma as well as a bit vector action, which is a Boolean function from b to the m to b to the n. Also note that if we have a state with several incoming transitions, then the bit vectors from the incoming states are combined using the bitwise OR operation. Entering the loop corresponds to creating a bit vector which is 0 everywhere except for the lowest position where it's equal to 1. Repeating the loop amounts to shifting the bit vector by 1 position, and exiting the loop corresponds to checking that the bit vector has at least 1 bit equal to 1 from position M to position N. For the example that you see on the slide, naive NBVA simulation has time complexity theta of n per symbol, where n is the upper repetition bound. This is because of the complexity of copying bit vectors and performing the bitwise OR operation. So the question we want to answer now is whether it is possible to do better than this time-wise. So indeed we can, and we propose an algorithm for which time per symbol is independent of the repetition bound n. And the main idea behind this is a technique for the efficient manipulation of bit vectors. I will show the key ideas of the algorithm by example, and to simplify things a little bit, let us consider both the lower bound and the upper repetition bound to be equal to n. The algorithm will focus on what happens on the states of the loop, namely Q2, Q3, and Q4. The algorithm maintains 3 bit vectors, V2, V3, and V4, all of size n, where Vi is the bit vector that belongs to the state Qi. All of these bit vectors are initialized to 0. Now let's look at the function update, which describes what happens when the symbol A is consumed. Looking at the pseudocode, the first step is what I call a rotation of the bit vectors. So this is just moving the bit vectors along the arrows of the automaton. The next step is shifting V2 by 1 position. Then we check if the incoming edge carries a non-zero bit vector, and if so, we set the lowest position of V2 to 1. Then for every I from 2 to 4, we check whether the symbol A belongs to the character class sigma I. If not, we set Vi to 0. Finally, update returns the value of the bit vector V4 at position n. Let's discuss the time complexity of this procedure. Notice that the rotation of bit vectors can be done in constant time using pointers. Also notice that the update function uses several bit vector operations, including shifting a bit vector by 1 position, setting the lowest bit of a bit vector to 1, setting an entire bit vector to 0, and reading a specific bit from a vector. A key idea is that all these operations can be supported in constant time using a data structure that is essentially a resizable circular n-bit array. So more details on this can be found in the paper. The main theorem is that the repetition of sigma 1, sigma 2, up to sigma k from m to n times can be evaluated in any context with time complexity big O of k per symbol, which is independent of the repetition bounds. In fact, our efficient algorithm can be generalized to a broader class of regular expressions that cover the bounded repetition of a regex R, where R accepts only strings of some fixed length. We have implemented the BVA scan regex engine in Rust. BVA scan incorporates both our efficient algorithms for bounded repetition as well as several performance optimizations. In particular, it uses bit parallelism to speed up bit vector operations for NBVA simulation, and it also integrates efficient algorithms for string search, which is a very common but much easier special case of regex matching. You can see now on the slide the plots for two micro benchmarks where we compare BVA scan against PCRE, RE2, and CA. We use two regular expressions that allow us to focus just on the performance of the algorithms. The main observation is that BVA scan has running time which is independent of the repetition bound k. PCRE and RE2, on the other hand, time out. Finally, notice that CA cannot support the second regex. We have also used several benchmarks that are representative of real application domains, including network intrusion detection, bioinformatics, spam detection, as well as malware and virus detection. Take a look at the plots at the bottom of the slide. If a point is below the diagonal, that means that our engine, BVA scan, is faster than the competing engine. We consider, as before, CA, PCRE, and RE2. So notice in these plots that BVA scan is faster than the competition in the vast majority of regular expressions. I'm just showing the results for Snort. The results are pretty similar for all the data sets that we have considered. Now take a look at the table in the middle of the slide. The key thing to notice here is that the average speedup of BVA scan over other engines is at least 10x. You can find more experimental results in our paper. Now I'd like to conclude with a summary of the main contributions of our work. We have introduced the new model of non-deterministic bit vector automata, which is a succinct automata model for regular patterns with bounded repetition. We have proposed new NBVA-based algorithms for the efficient matching of regular expressions with bounded repetition. The main result is that the time complexity of our algorithms is independent of the repetition bounds. We have also implemented the BVA scan regex engine, which incorporates the algorithms as well as several other useful performance optimizations. And finally, we have experimental results that show that BVA scan has good performance against PCRE, RE2, and CA over the workloads that we have considered. And with this, I'd like to conclude my talk. Thank you for your attention.
If you have a question, please step up to the microphone.
Hi. So my question is about, maybe I missed it, but you showed a model initially but with a counter, and then you switched to bit vector. So
that's right.
Why did you not use a counter model? Why did you need the bit vector?
We are using counters. They're just represented using bit vectors. And the reason behind that is that they can be manipulated efficiently.
But the integral counters, you think they cannot be manipulated
Right.
effectively?
Right. So let me go back.
Yep.
So you are talking about the relationship between the NCAs and the NBVAs.
You're disconnected already from the screen.
Oh, okay. Okay, I guess
You can just say maybe, it's fine.
Yeah, so the idea is that a bit vector can compactly represent a set of different counter values. So these two are equivalent things. And algorithmically speaking, using bit vectors is advantageous, both because it allows us to describe the algorithm more effectively, but also because we can use bit parallelism. So this is a performance optimization on modern CPUs because we have registers that can manipulate many bits at the same time. So this representation allows us to do much more work using just a few operations of the CPU.
Okay.
Right, so it's both conceptually useful and also very useful for an efficient implementation on the CPU.
Okay, thank you.
All right, please join me in thanking the speaker. I encourage you to ask your questions after the session. We move on to bidirectional object-oriented programming.
Hello, everyone. I'm Xin Zhang from Peking University in China. The title of our work is Bidirectional Object-Oriented Programming Towards Programmatic and Direct Manipulation of Objects. This is a joint work with Guanchen Guo, Xiaohe, and Zheng Jianghu. Bidirectional programming has two directions. In one direction, users can forward evaluate the input to get the output. In the other direction, users can also modify the output and apply a backward evaluation to the original input and the updated output to get the updated input. For example, we can forward evaluate the left source program to get the right menu bar. Then we can modify the Excel menu item from gray to blue. So the backward evaluation can automatically change the gray to blue in the left program. As a result, this updated program can run again to get this updated output. Researchers have developed many useful languages to achieve bidirectional programming, such as LittleLeo, BiX, and lens combinators. They are all functional or relational. As far as we know, there is no study on widely used object-oriented languages. However, in practice, object-oriented languages, many developers are used to develop software such as GUIs using object-oriented languages. So our goal is to design a bidirectional object-oriented language. Object-oriented languages are more complex because of two features. First, they have class inheritance hierarchies. Second, most object-oriented languages are not pure and have references. These two features bring two challenges. So I'll show the challenges concretely using an example. The first challenge is how to handle ambiguity in class hierarchy updating. On the left is a Java-like program. It evaluates to the right menu bar. So in the left, menu class extends the menu item class, and file menu is a menu object, and it invokes the setTitle method, which is inherited from menu item class. This method concatenates this argument T with 3 dots. So this method invocation will generate this file F and 3 dots on the right. Then, if we modify the 3 dots to a square bracket, there are several ways to update the class hierarchy to accommodate this update on the output. First, we can changing the setTitle method in menu item by changing the 3 dots to a square bracket, which is the most straightforward solution. Second, we can also add an overriding setTitle method to menu class, which concatenates the argument T with a square bracket. In this way, a file menu will call the overriding setTitle method here. Third, we can also add a new subclass named child menu to extend the menu class and override this new setTitle method. And then we also need to change the type of the file menu from menu class to child menu class. In this way, file menu will call the setTitle method defined in the child menu class, right? Through this example, you can see there is a huge ambiguity in class hierarchy updating, so it is essential to reduce it. The second challenge is how to handle references. In the same example, color is a reference that can be read and written many times and can be accessed anywhere in the program. So here is just a simple demonstration. Okay. So color is assigned white here, and the file menu uses it to set its color. Then color is overwritten to gray, and this Excel menu item uses it to set its color. So if we change the color of Excel item from gray to blue, we need to find a correct way to reverse the reference computation in the left program, and we need to pay attention to the update order and find which assignment should be updated, right? So we address these two challenges, and our main technical contributions can be summarized as these three things. First, we propose a novel bidirectional object-oriented language called BiFJ. We give a new backward semantics that can propagate the updates on the output to those on the source program, where we address the challenges of updating class hierarchies and references. We also prove its correctness. Second, we implement a prototype programming tool called BiOop to support our language for developing HTML web pages. Third, we demonstrate the usefulness of our language and our tool by successfully bidirectionalizing 11 classic object-oriented applications from a Java Swing tutorial and from GitHub. So now let me introduce how we design our language BiFJ. As the name suggests, BiFJ is derived from a core object-oriented language called Federated Java. Its forward semantics can be found in the book, The Types and Programming Languages. Based on these forward semantics, we give a backward semantics for it, and we prove its correctness. Then we extend this federated Java with references, and its forward semantics can also be found in this same book. And we give a backward evaluation semantics for it and prove its correctness. So these two bidirectional evaluation semantics are our main contributions. Now I'll talk about how to address the challenges. This is about handling ambiguity in class hierarchy updating. Note that we use this class diagram to represent class definitions in the above example. Specifically, the menu class extends the menu item class, which has a method called setTitle returning an expression T1. After backward updating this method invocation, that a menu object invokes this setTitle method. This left class hierarchy changes to the right one. Next, I will explain how this changes. First, we use a simple strategy called subclassing to create a new subclass named child menu to extend the menu class and override the setTitle method with a new definition T2. Then we optimize this class hierarchy to reduce minimize the changes, and in two steps. First, pull-up methods will lift methods from subclasses to superclasses. For example, we may pull up this setTitle method from child menu to menu class, right? Then we can also continue to pull up this method setTitle from menu class to menu item class. The second step is called collapse hierarchy, which removes empty, newly created classes. We think this is better for developers to understand because the number of newly added classes and methods is reduced. Finally, we prove the correctness in 2 steps. First, we prove the subclassing strategy is correct. Then we prove this optimization will not change the program's behavior, so it is also correct. Okay, then I explain how to handle references with an example. So this is an initial state which maps references to values, A to 1, B to 2, and LS to an empty list. A colon and an equal sign indicates assignment, and these exclamation marks indicates reading references value from the state. So this code means assigning a list construction of a B's value and LS value to LS. So after this, LS becomes a list of 2, and we assign A's value to B, so B becomes 1 here, and again, we repeat this assignment, so LS becomes a list of 1 and 2. Finally, we output LS, so we get a list of 1 and 2, and this step doesn't change the state. Okay, and we may want to change the first element of this list from 1 to 10, for example, and we propagate these updates back to the program. The big idea is straightforward. It is just to reverse the forward reference computation. And for example, in this last piece of code, we read LS value from the state. So here, LS value should be a list of 10 and 2. And the next, for this assignment, if we want LS value to be a list of 10 and 2, before this, B's value should be 10, and LS should be a list of 2. Okay, the next step is the trickiest one. So we can easily compute that A's value should be 10 before executing this. However, there is another thing to do. Because we know before this assignment, B's value should be 2 according to this forward evaluation. So we should roll back B's value from 10 to 2. Okay, so finally, LS value becomes an empty list. So to sum up, the important trick is to roll back reference values when we're encountering assignments. And for example, if we don't roll back B's value from 10 to 2, and which means in the initial state B is still 10, then we will output a list of 10, 10 instead of 10, 2. Okay? So these are the formalisms. You can read our paper for a more detailed explanation. And we also implement a prototype programming tool named ByOop to support our language. And to support directly manipulating an object structure produced by the source program, we adopt a 2-stage bidirectionalization. One is between the source object-oriented program and the object structure, and another is between the object structure with the actual output representations such as HTML code. So the first one, bidirectional transformation, is the core of our work, and just discussed. So for the second one, we build the correspondence between the object structure and the HTML code by adding structure information. Then in the evaluation, we collect 11 classic benchmark programs of a Java Swing tutorial and reproduce them using ByOop to demonstrate. Our tool can be used to develop typical GUI programs. So second, to demonstrate the effectiveness of our tool, we conduct a performance experiment by measuring the execution time for the 11 benchmark programs. According to the result, both the execution time of the forward evaluation and the backward evaluation are acceptable. So To sum up, we present the first object-oriented language that can support programmatic and direct manipulation of objects. Theoretically, we carefully extend a core object-oriented language with a backward updating semantics for clause hierarchies and references. Practically, we developed a tool called ByOop for generating HTML documents. We evaluate the usefulness of our tool by reproducing 11 classic object-oriented applications of Java Swing. That's all. Thanks for listening.
Again, please step up to the microphone if you want to ask a question.
So thanks for talk. So you, in the example you mentioned in the references, you showed that you can reverse like the semantics of the list counts. And I believe that if you want to do the same for like other operators, you have to more or less understand their semantics. And also I think sometimes maybe the reversing is ambiguous, like maybe there are possible ways to reverse it. So how do you handle this kind of like ambiguity, and also how the user can specify, or how you know that the reverse semantic of a certain operator?
Yeah, the ambiguity in the backward updating is an important problem in this bidirectional programming scenario. And but maybe this is not our focus in this work. And one way we can search all solutions for the updated program. And in my work, we use a fixed heuristic strategy for like arithmetic expressions. Yeah, so, but this is not our focus in this work.
Mm-hmm. So actually you just pick one possible solution.
For example, when we updating an addition expression, so there may be many solutions. For example, we can update the first operand, and or we can update the second operand, or we can update both. So in our work, we just choose one solution,
Okay.
but maybe we can search all solutions.
Yeah. And a follow-up question is, for example, if I want to reverse a function call, so
Yeah.
because maybe this function is defined as a customized, because that's user-defined method. So is it possible to also reverse this?
You mean what are the specialities?
The point is that if you have like the result of a method invocation, and now I think intuitively the reverse is to guess what should the parameters be, the input of this method be. So is it that possible to infer that in this framework?
So actually, the backward updating for function calls is deterministic, and there is no special things for it. We just update the function body first, and then we update the function and the parameters after that. Which means we propagate the updates in the function bodies to arguments and the function definitions.
Yeah, thank you.
Thank you.
The next talk is about bringing your own data structures to Datalog, and it's one of the papers that received the Distinguished Paper Award at Uppsala this year.
All right. Please make anxious-looking faces if the slides are not matching up with what I'm speaking. All right, so for the last few years, my collaborators and students and I have been working on building sort of state-of-the-art data log engines and trying to figure out, primarily for the purposes of things like program analysis, but also social media mining and graph mining applications, that sort of things. So what is data log? Datalog is a sort of reduced logic programming language. It's essentially just positive horn clauses over atomic literals. There can be negative variables, or negative predicates, but only if they can be stratified. So we'll just focus on this small fragment for now. So here are two example rules. So the first one says that when there's an edge between x and y, there's also a path between x and y. The second rule says whenever there's a path between x and y, and there's an edge from y to z, then there's a path between x and z. And so Datalog is an extension of SQL to handle recursive predicates and recursive rules. So the first rule is just plain old SQL. So here you can imagine that we're setting path to be everything from edge and basically saying copy everything from edge into path. Now the second rule is sort of a recursive or inductive rule. And we can't write this using SQL. Well, we kind of can if we use some extensions, but those extensions are not really going to be good for our purposes. They're a little bit too slow. SQL engines aren't really made to handle these kinds of heavily recursive queries. That's what Datalog is for. So the second rule is going to be evaluated in a fixed point loop. And the idea is that every iteration of the loop, we're going to join path and edge. We're going to get some new sort of transitive paths, and we're going to join those into path as well. So the first iteration, for example, will give us the 2-hop edges, and then 3-hop edges, and 4-hop edges, and then eventually we'll hit a fixed point just because the sort of graph number of possible edges between things and transitive edges is finite. But of course, if we remember our sort of high school abstract interpretation class, you can remember that if we sort of rediscover edges a whole bunch, then that's going to lead us to do asymptotically more work. And so the thing that I just talked about is called the naive evaluation strategy. And of course, we don't want to be naive. We want to only be semi-naive. And so the fix is that we compute basically these delta relations, or something like a frontier semantics, so that path delta is tracking all the edges discovered in the most recent iteration. And so the idea sort of here in Keynote is that you take all of the things that, basically you take the black edges, you turn up their opacity, and then you take this delta relation, and then you do only this join, but you ignore all of the stuff that's opaque, the orange stuff that's not from the previous generations. And of course, you get some more transitive edges, and keep doing that until you reach a fixed point. All right, so if Datalog is just this relatively simple Hornsat kind of sort of logic, not even nearly Prolog, for example, nothing like the cut, no backtracking, anything like that. Why does anybody care about it? Why is it useful? Oops. So the observation is that actually this kind of forward reachability at extremely high scale, which Datalog is really good at for some reasons that I'll talk about later, is very useful for a bunch of different examples. So for example, program analysis, the top program analysis engines in the world right now, at least of a certain style, are written using Datalog engines. And so you can get orders of magnitude less code compared to, for example, Walla or Soot or something like that. You can write them in several thousand lines just for a complete implementation of a whole analysis of, for example, Java. In the case of DUP, DDASASM is the most accurate, precise disassembler currently known, and CSerializer is an analysis of LLVM. You can also do things like graph and social media mining, so transitive closure, k-click, things like that. And also recursive aggregation, which is an extension of Datalog to put sort of reachability in a loop with an aggregation operation, so things like shortest path and PageRank and things like that. So Datalog's restrictions enable lots of modern implementations to leverage sort of several tricks that give us extreme speed. So the semi-naive evaluation, indexing is also very important, parallelization, very key, and efficient tuple representations with respect to things like locking and space-efficient representation. And modern engines really need all of these to be performant. So the state of the art is nested loop joins with explicit representations. Previously, we tried to use BDDs back in the 90s and early 2000s. They had variable ordering issues. Then we've kind of found that more recently, these explicit representations with good optimal indexing works very well. So what's the catch? Seems like it works really great in many circumstances. But of course, Reynolds tells us that whenever you implement something in a language, you inherit that language's features. And so the data structures that the engine provides, if you're implementing an analysis or something, some kind of analytics in the engine, the data structures can be leaky abstractions when there's an impedance mismatch between what the engine provides and what you need to use. So for example, let's think about 2 clicks and this transitive closure case. Well, unfortunately, we end up with something like this. And so, if this is not what you want, maybe not so good. But it's not just these graph operations. A similar extension of the little picture I just showed shows us why we can't do Steensgaard-style analyses in Datalog either. So some modern engines try to assuage this by offering us a sort of fixed set of data structures that we can choose from. But of course, that only goes so far. If you're not an author of the engine, then you have to expend a whole bunch of time figuring out how to extend the engine. I've spent a good amount of time trying to figure out how to extend Soufflé, but I don't like C++ much myself. So we present a new approach called Bring Your Own Data Structures. In Biodes, you can write something like this. So you specify that we want to use the transitive union-free relations, and that will make sure that this turns into this. And this TRRL UF is backed by a union-find-based data structure for transitive relations. So Biodes is a macro-based Rust-embedded DSL that compiles to Datalog to efficient kernels, which hook into user-provided data structures via an object protocol, realized programmatically via Rust traits. We have a formalism called DL sub DS, core formalism for harmonizing user-provided data structures with Datalog. And these are defined by something that's basically not quite Galois connection. There's not the round-tripping property required. This is important for some reasons we explained in the paper. So D has to be a lattice, and there's an injection function and a concretization function, and then you can define the naive semantics in terms of those, and everything kind of works out. And the theorem says that if all the concretization functions are monotonic, then so is the immediate consequence operator for the program as a whole. We give more details in the paper. It's one of those interruptions. Including a semi-naive semantics as well, which says sort of a characterization of what is required for these data structures. So we define this via a 2-stage protocol. The first is compile time, where macros specify sort of this formalization. So for example, the user has to specify rel ind macro, which computes the type of logical indices. This is called by the Biodes compiler to figure out indices as the compilation happens. Rel ind common computes the carrier type. It's actually going to represent these tuples. So for example, if I define a relation, this little hash and then ds myProvider says use the myProvider sort of representation. I'm defining this relation foo with 2 columns. And then Biodes will invoke the data structure's rel ind common macro, which will then cook up a representation for the carrier type. And the data structure providers can use arbitrarily complex logic to construct types for relations and indices. For example, we implement Soufflé's optimal index selection, which is a major pass and innovation in the Soufflé engine that we were able to implement just in our library in Rust. The second stage is runtime. So relation backing data structures have to implement 4 Rust traits. Rel index read, which reads from an index. Rel index read all, which iterates over a relation. Write, which writes to an index. Rel index merge, which does semi-naive evaluation or merges things in at the end of the loop. We built Biodes to be an extension of Ascent, which was a previous Datalog engine that we built in Rust. It did not have parallelization, it was just serial, worked with kind of a traditional strategy. It implements a fully featured state-of-the-art Datalog that's competitive with Soufflé and all the other engines that you sort of probably know and love, including parallelization using Rust's Rayon and work stealing. And we observe performance on par with Soufflé. Frankly, I think it's better than Soufflé, although I can't claim that it's universally better. Soufflé has lots of good innovations. For example, Soufflé has feedback-directed join planning, and they've done a lot of innovation in that space, which we haven't done. We'd like to integrate that into Biodes someday. So let me show some results. So we re-implemented Polonius, which is an implementation of the Rust borrow checker currently being implemented by the Rust working group and trying to be used in the Rust compiler. I think maybe it even is right now. We've implemented this in Biodes. And we compared using explicit versus transitive relations versus index sharing. Transitive relations give us a 2x speedup and a 1.5 to 2x compaction in memory. This is single-threaded. The way that Polonius is written, there's not very much parallelism to exploit. So we tried running it in parallel. It didn't really help. And it's also, everything runs pretty fast, at least in these experiments. Index sharing means more write contention, so it's going to be more compact, but you're going to be sort of writing across things. Not such a big deal here, but we're going to see it more later. So we tried doing transitive closure via union find, so the catastrophic picture I showed earlier. We see time improvements of up to 10x and memory improvements of up to 30x, and of course this is going to depend on the dynamics of the graph. If you have a graph that's very sparse, has very few clicks, then this isn't going to help you very much. We get extremely good parallel results. This is not a direct property of BIODES itself, but it's more just evidence that BIODES can sort of integrate with high-performance modern implementations. My experience is that Soufflé scales to roughly 4 to 8 threads because of the way the data structures are designed. BIODES uses Rayon's work stealing, and we're able to see very nice performance. This is a 32-core, 64-thread server, and the thing I think is really exciting about this experiment, PageRank, which shows an extension. It's not just sort of Hornsat reachability, it's also lattices, because you need to be able to do monotonic updating. So the thing that I think is really exciting here is that the bigger the problem gets, the more parallelism there is to extract. So you can see at 64 threads, we get a roughly 40x speed up on the largest graph with, let's see, 4.3 million nodes. And last, we paired with some of our partners at Galois, and we have used BIODES to implement one of the, at least in my mind, very robust sound analyses of LLVM. So it's a 2,500 line, roughly, analysis of LLVM in a combination of BIODES and Rust. The thing that's really exciting to me here is that it's really written the way that you would actually want to write the analysis. You don't have to do a whole bunch of massaging to throw things into Soufflé or some other engine. You can use the most popular LLVM parsing library in Rust and throw things directly into BIODES without any extra work. Our analysis is an Anderson-style MCFA, so the M-top stack frames, and it follows the abstracting abstract machines approach. Comparable to CCLyzer, CCLyzer is not sound. It's designed to be more precise, but we found that the soundness, or the lack of soundness, is a serious issue in practice. But YAPAL is. And we also measure the impact of index sharing. The thing that's most exciting to me here is that using this approach, we can complete a one-context sensitive analysis of HTTPD, enumerating 5.3 billion control flow points in 7.3 hours at 8 threads, and 2.7 hours at 32 threads. If we use optimal index sharing, it cuts the memory in half, and it allows us to compute an analysis of HTTPD, which otherwise just blows up and doesn't terminate on our 512 gigabyte server. Now, the index sharing is not universally good. It does induce more write contention, because since you're sharing more, there's going to be more times where you're going to be waiting on trying to update a data structure. And so, for example, we can see over here on the sort of smaller program, Jackson, at 8 threads, we can see it's 8 seconds versus 10 for the default. Default is without index sharing, meaning there's more copies of things, but you've got worse sort of memory performance. But in Redis, for example, using index sharing, it's 19,000 seconds versus 11,000 seconds. So, yeah. So thanks so much. The thing that we've tried to show here is that it's possible to get state-of-the-art data log performance as a library, but the engine's data structures become leaky abstractions. Instead, we propose bringing your own data structures. Ascent is now public. We've integrated the ideas from BIODES into Ascent, and more of them are being backported, although there's also an artifact you can look at. YAPAL, the pointer analysis that I mentioned, is also open source and public, open source by Galois recently, and I would encourage you to take a look at that as well. And I'd like to end by saying that this is not primarily my work. I helped Arash do the writing. I'm his advisor, but primarily this is the work of my student, Arash Sahib Al-Amri, who's now graduated and working in industry. So thanks so much.
Thanks for the great talk. What about negation? Can I write a data structure that uses negation inside? And can I use a data structure in a program that uses negation?
All the typical negation. I'd love to. That's, you know, I have an NSF grant that we said we were going to do that in, so let's hope we can.
All right. If in 3 years you haven't done it, I'm going to be on your neck.
Yeah, I'll have to report back to the government.
Have you discovered any data structures you cannot abstract by lattices, right?
Oh, that's a great question. Well, I guess I would say you're constrained that it has to be represented as a relation. So one thing I would say that I think is kind of not so great about this work is that there's some other really nice work out there called Egglog by Max Woolsey and folks. And they have a better story in terms of how joins get performed. We have to materialize whenever we perform a join, and there are some tricks that they can play. Those tricks don't generalize very well across different data structures, so our work is kind of, you know, more general, I guess, not just union find. But we don't get as good performance as Egglog in some specific cases asymptotically, although, you know, they don't support things like parallelization and, you know, Rust and things like that. Well, I guess, you know, yeah.
Is there time for another question? Or?
No.
No. Okay.
Sorry, let's thank the speaker again. The last talk of the session is about new macrosystem for Racket.
Yeah, it's about Rhombus, which is a new language built on top of Racket. If you do know Racket, then I can summarize the goal of Rhombus as making Racket's macro technology more accessible. Accessible means a bunch of things here, but the most notable thing it means is changing the notation to more conventional. Arithmetic looks like arithmetic. Function calls look like function calls. Array and field access look like array and field access. That's as opposed to parenthesized prefix notation. All right, if you don't know Racket, let me remind you what we're trying to keep here. Racket is about language-oriented programming, so that can mean using a little DSL where your program needs to parse or have a compiler pass or extend data log with data structures. It can mean adjusting a general purpose programming language so it's better for building web applications or writing slides, or it can mean making a whole new language that's just for writing one kind of video game. So in all of these cases, we want some language that better fits the domain. And we all know how to make programming languages. You parse the source into some AST, and then you compile it into machine code, and that's a lot of work. So a good shorthand, shortcut is to use a target language, and that's higher level instead of machine code, right? Something that's maybe close to the language that you're working on. An even better shortcut, because you know, here you still have to adjust your tool chain and update all those parts. So a better shortcut is if your target language has in it a way to update the front end. And that's what a macro system is. And for the purposes of today's talk, we'll call this the big Lisp idea, being able to extend that front end to add things into your language. And it was refined in Scheme and made to work better with modules and so on. But sometimes you don't just want to extend a language, you want to have a smaller language, or you want to make a completely different language, so you need something else. And in Racket, you do this with #ling at the beginning of your program. And that's a kind of import that starts off everything, so you get to pick everything that's in your language from the beginning, right? And we'll call this the big Racket idea for today's purpose. That and having enough facilities in your macro toolbox to make use of that and build up whole new languages. So that's a way you can build a programming language. We think it's a good way to build a language because this technique scales for very small problems like where you just want to avoid some boilerplate or repeated code, to when you really want to make an abstraction for a particular domain in a library. That's what we normally have in mind with language-oriented programming, to making a whole new language. Right? And it's the same toolbox that we can use for all of these problems, so we can provide a path from doing something simple to more complicated to building up this whole new language. Even in Racket, with this hashling mechanism, you're not constrained to parentheses. You get to pick the character parsing at that level. But most of the facilities you get in Racket are really oriented around manipulating S expressions, manipulating these parenthesized terms. And so that's why there's room for more support from the language like Rhombus. So now let me finally show you what some Rhombus code looks like. Here is Rhombus class declarations with some extensions to make subclasses. But if you're defining an expression-based class and Lambda and application variable subclasses, probably you're making an interpreter, and you'd really like to write it ML style like this, right? Like to write data type expr and the 3 different variants there. So in Rhombus, we can get from the code on the right to the code on the left using this data type macro. So defin.macro is defining the macro. The quotes are not strings. The quotes are code quotes. So inside is still structured, the same as outside. $sign is an escape. So an escape in a pattern is binding the pattern variable like type. And then $sign in the template, the result part, is escaping to refer to those bindings. And the ... is not where I left things out of the code. That's the actual code. ... means repetitions on the pattern side and on the generation side. Okay. So probably you didn't really need much explanation of that macro. It's supposed to be pretty easy to read. If I have that data type, I might write a type of function that's working with it. And in Rhombus, everywhere that there's a binding position, like the argument of a function, it's also a pattern matching position. Or you can put annotations, like here I've annotated gamma with environment, which has certain runtime and static associations. But really, both of these things are just an artifact of binding positions being macro extensible. So it's just that things like a lambda constructor can act as a pattern form in a binding position. And so if we want to make our own notation here, maybe we want type of to take its arguments with a turnstile in between, then we can define our own binding operator here, which is another macro, just written for bindings as opposed to definitions or expressions. So here I'm defining turnstile binding to take its 2 pieces, expression and environment, and putting it together in a list with square brackets. So I'm expecting a list at least. I'm pattern matching on that. So that changed the protocol. And where I'm calling type of, now I need to use a turnstile also. But this is a different one. This is an expression position. So I need another macro that cooperates with the bind macro that takes expression and environment and puts them into a list as it's expected. Okay. So there are these different kinds of contexts, different spaces like expressions and bindings and annotation and quite a few more. And of course, you want to be able to define your own kinds of positions like this. So maybe you want to put regular expressions in your program and you want to use operators like plus and question mark and star as they mean and as they have precedence and so on in usual regex notation. Right? And you can do that by defining your own library that's going to define regex and the sublanguage inside of it. And the way you define that library, well, that's the rhombus space.inforest form that there's a lot here that we can't look at. But the big picture is there's a way to instantiate a new sublanguage, like regex. And when you instantiate it, you get a way to go into that space from some other form, like the expression macro rx here can get into the regex meta world. And then you also get a form for populating that instantiated subspace. So regex.macro here, so I can define star and question mark and plus and so on for my regex language. Okay. So hopefully you get the idea that gives you some sense, I hope, of what Rhombus can do. Some of this may look new and some of it you've seen before, right? We're building on a lot of existing work, and Rhombus is in many ways a synthesis of work from the Lisp and Scheme and Racket communities. Also, it's not the first time you've seen macros without parentheses, so there's a lot of other languages out there that do it. So to try to explain more where Rhombus sits, let's go back to our pipeline picture. So the simplest forms of macros are ones that just work, rewriting the source text. I'm thinking of the C preprocessor and so on. There are well-known problems here about maintaining expression integrity and so on. So modern macro systems don't do that. Many of them work at the abstract syntax level. So this is where template Haskell, OCaml PPX, Elixir, Scala, and so on, where they all sit. And so the advantage here is now you're manipulating something that has some structure that's better defined. A small drawback, though, is that any new form has to masquerade as some existing form in the core language until it gets desugared, usually as a function call, but still it's a kind of constraint. Lisp doesn't work that way. It introduces this new intermediate form, S expressions, of course, in Lisp, which is in between the text and the abstract syntax. And other languages have things like this. So Rust has token trees. And Rhombus, as you see, has shrubbery. That's another notation in this category. So usually we think of macros in Lisp working, sort of taking S expressions and rewriting S expressions. It's not quite right to put the loop there, though. Really, macro expansion happens in the frontier of AST parsing. So macro expansion is more like this. In Lisp and in the successors that work in the same way, like Scheme, Racket. I'll put Rust in the same category, and Rhombus. Then we start to distinguish later evolutions from Lisp, like in Scheme and later languages. We take S expressions and add context information, binding information to it, so that we can have lexically scope macros, or hygienic macros is a better phrase, maybe. And then Racket, maybe we go a little farther than Scheme, and that giving you more control over this interplay of expansion and AST parsing to force parsing of sub-expressions, or in Rust, you can say, take this token tree and parse it as an expression for me. And then in Rhombus, we go a little further, and we have these different sub-languages. So you can say, take this token tree and parse it as a binding or as a regexp or something like that. Okay. So that's one sort of line we might draw through things to distinguish Rhombus. The paper goes through 4 more general areas to position Rhombus, and I'll spend the rest of my time just giving a brief summary of those 4 different areas. Okay. The first is this replacement for S expressions that we call shrubbery, but S expressions, everything is grouped by parentheses. All grouping is explicit and using parentheses. The advantage is we have a very simple grammar for S expressions. You're either an atom, which is like a symbol or a string or a number, or you're a sequence, a parenthesized sequence of those kinds of terms. Right? So the advantage here is a very minimal grammar. The disadvantage is, well, there are an awful lot of parentheses. And because there are a lot of parentheses, there are many proposals out there to group S expressions in different ways using white space or other notation. But what most of these have in common is they're still representing S expressions. And it's not really the parentheses that are limiting, it's often the minimalism of this AST that's limiting. So what we do in Rhombus with shrubbery notation is that we have more ways of grouping things. So a pretty natural one is that things on the same line are grouped together. So it is white space sensitive. In some other contexts, some other cases, things might be separated by commas, say in parentheses. But parentheses don't turn off the other modes, so you can still nest things with white space and lines inside of parentheses. But another important feature of this notation is that it doesn't try to group everything. And this is why it's a shrubbery. It hasn't yet grown and fully formed into trees with everything grouped just yet. That will be part of a later parsing step. And that parsing step can be sensitive to bindings and precedence as determined by bindings and so on. So the way it works out is we end up with this kind of grammar for the representation of shrubberies. And you see it's bigger than S expressions, but still way smaller than ASTs. And you can see the papers for the details of the particular white space sensitive rules that we have, but it's maybe more important about the size of this grammar and where we're exploring this point. So that extra parsing step that's left, where we have to go from something that has traditional sort of infix, that is called inforestation. Right? We're growing it into a full tree, and that has to be interleaved with AST parsing and macro expansion because binding is involved here. So you end up with really 3 points in that cycle of macro expansion. The paper does provide a model of inforestation that's building on one that we had before for the language Honu. And of course, I will leave that to the paper. Earlier, we saw that in this parsing, it can be sensitive to the context, right? We had expression macros and binding macros and other forms. The way that this works in Rhombus is that it builds on Racket's notion of scope. So you can think of a scope on identifiers as being a color that we put on it. That's going to help us distinguish different bindings for different nestings and so on. So since all of this code started in the same module, it might start all as blue. But what Rhombus does is it designates a particular scope or color for expressions and a particular scope for bindings. And so when we define the expression macro turnstile, its identifier gets this extra color to say I am an expression. right? And the one for bindings gets an extra color to say I'm for bindings. And then when we find a turnstile that's in a binding position, we add the binding scope to it, and that way we find the right macro definition to expand that binding position. Whereas a turnstile that's in an expression position, we'll get the pink color here, and so we'll know it's an expression. Well, I should say I'm oversimplifying here a little bit. And you can see, again, the paper for some details. But this using scopes as opposed to name mangling not only works well with macros, it just works out better in general. Rhombus has support for static information. So here I'm defining a class posin that has an x and y field, and I've got a function that takes PS, which is a list of those. And when I use the indexing operator on that list PS inside the function, it's statically resolved to be list lookup as opposed to array or more general sequence lookup. And similarly, this dot accesses the x field of a posin, not just the x of any particular object that happens to have an x field. Right? And the way that works is, well, there's this annotation sublanguage where you can say things like list of posin, which is kicked off by the : annotation binding operator. Right? And that operator gets static information from the annotation and associates it with the binding that it's creating, PS. So PS has that information, and the square bracket macro that's implementing list indexing can see that and know that it actually has a list. Furthermore, it can see it's a list of posin, so it propagates that information that the dot macro can see and say, oh, this is a posin, so X really means the posin X here, not just any old X. Right? So this is sort of, again, built into the macro system. It should remind you of a type system. It's not exactly a type system. It's a more general primitive thing that you can use to build up a type system. And to demonstrate that, we've actually done that. Ben Greenman and I in our class that we're teaching are using a language called SPLASH'23, which it's really ML. It's the core ML type system, but it looks like Rhombus, and it's implemented in Rhombus. So there's a little example of what it looks like down there. So it demonstrates that we can build a type system with inference inside. It makes good use of this static information system. It shows that the syntax generally works okay for people. It's worked well for our students. Predictably less trouble than parenthesized prefix notation overall. The students are not writing macros in this course, but they are manipulating terms, shrubbery terms, because the language that they're implementing is represented using shrubbery terms, and so they write little parsers, and sometimes the parsers have little desugaring rules in it that are macro-like. So again, it shows that manipulating shrubbery terms is tractable for people. Okay, so that's Rhombus in a nutshell. It's still early days production-wise, but it's working well enough that we can use it in a class. The idea overall is to take this racket technology, start with it so that we have good meta-programming facilities, adjust the notation so it's more, closer to what people want in many contexts, but also take what we've learned about best practices for using things like racket scope and its binding and looking up things at compile time and packaging them up into, out-of-the-box support for static information or extensible binding positions. Okay? And of course, see the paper for more detail. Thank you.
Please step up to the microphone if you want to ask a question.
Hi, thanks for a great talk. So when programming with a language that's completely based on parentheses notations, my editor often has some intuitions about how to properly format my code automatically. Even though I may be defining macros, if they still all work with parentheses, it might not be exactly what I want, but it has some idea. So how do you achieve the same sort of if indentation is significant, and how do you tell your language servers or your formatters how to work with the macros you just defined?
Right, so we do have support in Dr. Racket that uses a general protocol in Dr. Racket for communicating, so it's not far off from what a language server protocol would use, and we expect to get that working in general. But it's pretty standard, language servers often say, what should I do when I tab? How should I color things? Syntax coloring is, of course, an important thing here, just like parenthesis matching and offering all the tab possibilities as you cycle through with tab. So I think just because we've built it, I feel confident that it will generalize to existing, IDE interoperation things. Am I answering your question?
Thank you.
Okay.
Hi. You said that you could use this macro system to implement type systems. Do you have any thoughts on using it to teach type systems to students?
That is a good question. I don't. So what we're building on here is the types. Let's see, macros as type systems as macros. I forget which way it goes. Stephen Chang and others. We have done like summer schools where we teach how you can use this, but not try to teach type systems from scratch using this technique. So it's a thought, but I don't know the answer there. I think in that previous work, they had a domain-specific language that looked like traditional type rules, and that's probably the way to go, even if you're using this technology on the inside.
Thank you.
This concludes the session. Thank you very much. Thank
you.
Okay, it's fine if that's for you guys. Yes.
Giovanni, qual é o tema? Information flow. Okay. Hong Kong. Are you in Hong Kong?
Yeah, I'm in Hong Kong. Hong Kong. Longe. Longe de casa. Longe daqui.
Exato. Longe do Brasil.
É. Vários voos muito longos.
Sim, sim, sim. Não gostaria. Não gostaria. Pode ser giro, Hong Kong, Macau.
Start?
Yeah, sure.
Which one? Think wait another 2 minutes?
Yeah, I think.
Okay.
But no more than this.
Yeah, I don't want it to get too late. Okay.
Because people is coming, so.
Yeah, I still see people coming in, so we'll wait another 2 minutes.
I'm going to the door.
Okay.
Close it. Yeah.
Okay. Yeah, move wait another minute. We start at like 2:02 on my clock. Does that sound good? Okay, everyone, let's get the session started. Welcome. This is the first program analysis session of UPSLA. We have a very exciting set of talks. And the first is going to be by Giovanna Conrado. She's going to be telling us about the bounded path width of control flow graphs.
Okay. Hi, everyone. My name is Giovanna. I'm going to be presenting on the bounded path width of control flow graphs, which is a work I did with Amir Goharshadi and Chung Kint Lam. We're all from the Hong Kong University of Science and Technology. Okay, so I have a program. A program can also be written as a graph, a control flow graph. That's a graph representation of the program. The convenient thing about writing a program this way is that many compiler optimization tasks, they can be written as graph problems in our control flow graph. The problem is that these graph problems are very often very hard to solve. So something that we've been employing for a while now is these things called tree decompositions, which means that we're using the fact that these programs kind of look like trees. And by using the fact that they kind of look like trees, we can solve a lot of these graph problems way more efficiently. So this has been historically used to solve like register allocation, redundancy elimination, reducing cache misses, and all types of like data flow analysis tasks, like algebraic program analysis. And what we do in this paper is that we prove that these control flow graphs also kind of look like paths. And the nice thing about this type of decomposition is that we can solve all the same problems that we could before with the tree decomposition. The algorithms are much, much simpler because paths, arrays, are easier than trees. And also we can have very large speedups, even complexity speedups in some of these algorithms. Okay, so let's look at a more concrete example, something like register allocation. We want to know if we can map the variables in a program to registers without interference. So if I'm using the value of two variables at the same time, we cannot map them into the same register, otherwise we're going to be overriding values, right? And this problem actually maps to graph coloring, a variant of graph coloring in our control flow graph. Okay, that's amazing. Now we have to solve graph coloring, right? Graph coloring is not very easy to solve, so we want to know if a graph can be colored with a certain amount of colors in such a way that two adjacent vertices have different colors, and that problem is NP-complete, even for 3 colors, right? So we're not going to be solving any programs this way. Okay, so now we need to determine how do we solve these types of problems efficiently on control flow graphs. The main idea of this type of technique is that we want to prove that control flow graphs have a specific type of structure, that they have a specific type of shape. And now we can try to solve these hard graph problems efficiently when our graphs have that specific type of shape. Okay? So let's start by defining our control flow graphs a little bit more specifically. So control flow graphs are a graphical representation of a program. And here we're going to be focusing on intra-procedural program analysis. So that's program analysis within a single procedure, within a single function. We're not considering function calls. Many compiler optimization tasks, such as register allocation, are done in the function level, right? Okay, so here's a problem. Here's a program. And here is its control flow graph. The way that we transform this into this, each line or each comment of our program becomes a vertex in our control flow graph. And if one line can go to the other, then we put an edge here. So for example, here we have if 1b, then break 1, else alpha 1. If b is true, I'll go from if 1 to break 1. So we have this edge here. And if b is false, I'll go from if 1 to alpha 1. So we have this edge here. And by doing that, every execution of my program is going to be corresponding to a path in my control flow graph. So maybe if I'm taking like this while loop a couple of times, it's going to be like taking a cycle here, right? And I'll start in the beginning of the program and then at the end of it. And another concept that's going to be important for us is the nesting depth of a program. That's going to be the nestedness of a statement. You can think of it as like one atomic statement like alpha will have nesting depth of 0. If I put that inside an if, that has nesting depth of 1. If I put that inside a while, that has nesting depth of 2. Intuitively, it's going to be like the maximum number of tabs that you're going to use in your program, or like how wide your program gets. And if you write well-written code, you might think that like your program shouldn't be getting too wide, right? Your nesting depth should not be too high. And most coding standards actually discourage high nesting depth or just fully forbid it because it makes programs not very readable and generally not very efficient as well. Okay, now that we have our control flow graphs, we need to find how to solve graph coloring faster sometimes. And the idea here is that we're going to introduce a concept. So in this case, we're using path width, which is some measure of how simple a graph is. So this path width is going to be a number from 1 to n. And the smaller it is, the more simple the graph is. So a graph like this, that kind of looks like a path, is going to have low path width. A path has path width of 1. And a graph like this, that's more complicated, it's going to have high path width. The worst case is a click that has path width of n. Okay? And the idea here is that now we can formulate a graph coloring algorithm that has a complexity that looks something like this. So n times 3 to the path width. So if our graph is complicated, we still haven't solved graph coloring efficiently. We haven't proved that p equals np here. But if we have a simple graph, if we have a program of like constant path width, then we can solve graph coloring in linear time. Okay, so this is kind of the idea. What formally does this mean? How do we actually measure a graph similarity to a path? And we're going to be using something called a path decomposition. This is a sequence of subsets of vertices of my graph. You can think of it as if I'm walking through the graph, keeping a very small set of vertices. And we don't want this set of vertices to ever get too big. The set of vertices need to traverse all the possible edges of the graph. And whenever a vertex exits my set of vertices, I can never visit it again. So here I exit 1. I can never see 1 again, okay? So a bit more formally, a path decomposition is a sequence of bags of vertices of my original graph in such a way that all edges must be contained in some bag. So if I have an edge like 2, 3 here, there must be a bag that contains both vertices 2 and 3. And if I see the bags containing any particular vertex, that's contiguous. So if I look here at the bags containing vertex 3, that's going to be bags 2, 3, and 4. That's contiguous. I couldn't have, for example, vertex 3 being in bags 3 and 4, but not bag 3. Awesome. So the width of a path decomposition is going to be the size of the largest bag minus 1. As I said, I don't want these sets to ever get too large. So for example, for this path decomposition here, largest bag has 3 vertices. The width is going to be 2. And the path width is going to be the minimum width path decomposition of a graph. So over all possible path decompositions, which one has the minimum width? That's the path decomposition of a graph. We also have a similar concept called tree width, which is a graph similarity to a tree as opposed to a path. These are all things that are defined analogously. This is going to be a tree of bags of vertices. But the important thing here that I want you to notice is that a path is a tree. And just like a path is a tree, a path decomposition is a tree decomposition, right? So if I have a graph, and that graph has a path decomposition of width 5, then it also has a tree decomposition of width 5. But the reverse is not true. So this means that the tree width of a graph is always smaller or equal to the path width of a graph. So a graph having like constant tree width doesn't mean that the graph has constant path width, but a graph having constant path width means that the graph has constant tree width. And in fact, there are problems that we cannot solve efficiently if a graph has small tree width, but we can solve efficiently if we prove that the graph has small path width. Cool. Now, the nice thing, let's look at the path width of control flow graphs. What we're going to do is we're going to start with a control flow graph, and we're going to try to build a path decomposition of it. This is our path decomposition. So each one of these columns is going to be a bag. Each one of these lines represents a comment, which is a vertex in my control flow graph. And they intersect when a certain vertex is in the bag. And we want to know what's the width of this path decomposition. That's the maximum number of vertices in every bag, minus 1. Okay, so now we want to know, like, how do I get from here to here, right? How do I get from my program to a path decomposition? And I essentially need to handle 2 types of statements, when we concatenate 2 statements and when we nest statements. So let's do something like this, right? I have this if and I have this while, and I want to find the path decomposition of the concatenation of these 2 statements. What I'm going to do is I'm firstly going to recursively generate the path decomposition for each of the statements. So I can recursively find what's the path decomposition for this little if here. Then I find what's the path decomposition of this while. And now to find the path decomposition of the concatenation of them, I just put the 2 path decompositions together, okay? And I also need to add a little bag here in the middle. And this is to cover the edge from the end of the if to the beginning of the while. But the thing that I want you to notice here is that the width of the decomposition does not get larger. right? The maximum number of vertices in any bag is going to be the maximum number of vertices here and the maximum number of vertices here, and 2. And so when I concatenate statements, our path decomposition is not actually getting wider. We also have nested statements. So for example, what's going to be the path decomposition of this while here? Well, to do that, we'll firstly recursively generate the path decomposition for the inside statement, so for the if in this case. And then I'm going to add the vertices corresponding to the loop, which in this case is like this while2 and the done2 to all bags. This is so we can cover edges like breaks that map from the inside of the while statements to the done, and edges like in continuous where I map from the middle of the statement to the while. So I need to add these 2 vertices to everyone here. And here, the width of the decomposition increases by 2, because I am adding 2 vertices to all these bags, right? So what we have now is that every time we nest a statement, the width of the decomposition increases by 2. So the path width of a control flow graph is going to be at most twice its nesting depth. And as we said before, the nesting depth of programs tends to be constant, and thus the path width of a program is also constant. Little side note, gotos here can increase the path width. So for every goto, we're assuming structured programs which have no goto. If you have a code goto, the path width of your program is going to increase by at most 1, generally not much more than that. These things are a little bit better in practice. And also, something important is that we can obtain the path decomposition for the program in linear time. This is important because path decompositions are actually very hard to obtain in practice. But for control flow graphs, we can get a path decomposition very easily. And this is to contrast with the previous result, which was for the tree width of control flow graphs. And that was that control flow graphs of C have a tree width of at most 7. This number changes according to the language, but it's generally a constant. And it also increases by 1 every time we add a goto. OK, so now we can solve register allocation. We know that register allocation can be reduced to graph coloring. And this is going to be graph coloring on a graph of small path width. And now we just need to solve graph coloring on path decompositions. And this is essentially going to be a variant on graph coloring on an array. And we can solve it pretty straightforwardly with dynamic programming. OK, so now we can look at the register allocation problem. Our dynamic programming algorithm has this runtime here. And the previous tree width-based algorithm has this runtime. So as you can see on the exponent of the number of registers, ours is about half of this, right? It is the half if you ignore that these variables are different. Here, we're looking at the path width of a graph, and here we're looking at the tree width of a graph. And as we saw before, the tree width of a graph is always smaller than the path width. So which one of these is actually better? We don't know. Let's do experiments, OK? So we want to compare our algorithm with the tree width-based algorithm. And since both of these algorithms are exponential r, this is going to be the number of registers required, we need to find a data set with few registers. SDCC, the small device C compiler, kind of naturally fits into this. So it's compilers for microcontrollers. This is embedded systems. They naturally just have few registers. And so this is going to be the width of the tree decompositions and the path decompositions found. The lighter red here ones are the tree decompositions. And as you can see, the tree decompositions are smaller. That's expected. That's how things work. But the important thing that I want you guys to point out is that for both the tree decomposition and the path decomposition, they generally have a width of at most 3. So both the compositions are generally fairly small. And if we actually run the algorithms, we can see that our algorithms, which are these one in like a darker red here, our algorithms are here, theirs are here. Our algorithms actually run much faster. This is a logarithmic scale. So our algorithms for register allocations runs on average 800 times faster than the tree width-based one. So essentially, in practice, both path width and tree width of these programs are fairly small. And even though the path width is larger, that's much more than compensated by our complexity gains, and also the better hidden constants that work when you're working in an array instead of a tree. OK, so going to the final remarks. What's the point of this paper? Control flow graphs have a path width of at most twice its nesting depth. This is the paper. And why should you care about this? If you either heard about tree width or not, why do you care about that? Well, first of all, we like using path width because it's a stronger parameter. It's always nice to have stronger bounds for things. All tree decomposition-based algorithms still work if you just put a path decomposition instead. Because as I said before, a path decomposition is a tree decomposition. You can just plug in the new decomposition into your algorithm, and it might run faster. In fact, just the fact that you're plugging in a path decomposition might even improve the complexity of your code without you having to change your code whatsoever. The hidden constants on paths are better. You can do way more optimizations when you're working with array. Things can be much more cache efficient if we're working with arrays as opposed to trees. And also something I didn't mention is that our decomposition works for labeled breaks and continuous. So our bounds work for programs like Java, and that's not the case for the previous tree with base bounds. And also, like, what I want to drive, the point that I want to drive in this presentation is that it is just much simpler to use path decomposition algorithms. So if you work with control flow graphs at all, and you do algorithms on them, and you're not exploiting their structural properties, you're not exploiting the fact that these graphs are very simple, I feel like you're wasting a lot of potential. And the tree with decompositions, they might have been a little bit complicated to get into in the past. But if you ever wanted to exploit these properties, I think this is a very good moment to do it, because it's never been easier to actually exploit these properties of these graphs. Yeah, I think that's it. Read the paper. Thank you very much. Yeah, any questions?
Okay. If you have questions, please step up to the microphone. So I'll start things off with a question. I think the running times you were showing for the register allocation,
yeah,
we're getting up to what? Oh, this is microseconds. I couldn't read microseconds. Like,
yes.
On the higher ends, how long is this
10 to
running?
the 8 microseconds, and ours on the higher end are about 10 to the 5 microseconds.
So this is, I just wanted to understand, like I just saw 10 to the 8, this is practical to run in a typical optimizing compiler, or am I waiting hours for my program to compile?
I believe our algorithm is practical to run on a compiler. The previous algorithm wouldn't be. What they do use in regular SDCC is they use a hybrid variant of the tree with based algorithm with some heuristics. So you're not, both these algorithms that we're presenting are optimal. In the actual SDCC, you're not always guaranteed to get the optimal result, but they run much faster, like they compensate that by running faster. But I think our algorithms would possibly be practical.
Okay. No other questions? So I had one more.
Yeah.
One thing I didn't quite follow. You said that the tree width is going to be smaller than the path width, like with the best decomposition. But at the same time, you said that using a path decomposition might speed up your tree width based algorithms.
Yes.
So I couldn't quite follow how those two things could both be true.
Sure. So yeah, the tree width is smaller, but well, first of all, they are very often the same. And in case where they are the same, the path width based algorithms will run faster. And also when you're working with tree width, sometimes, especially in these dynamic algorithms, we have these types of like introduce nodes, erase nodes, and merge nodes. And sometimes handling these merge nodes are very costly. And these path decompositions don't have merge nodes. So you're essentially just not running a part of your algorithm that may take a long time if you use this particular type of input. That's why these algorithms can run faster complexity-wise.
Okay, great. Yeah, thank you very much.
Awesome, thank you.
Okay, let's thank the speaker again. Okay, so our next speaker is going to be Ben Greenman, and he's going to be telling us about their work on how profilers can help navigate type migration.
Excellent, thank you, Manu. All right, so this work was supported by the CRA. I was a postdoc. I have since graduated from the postdoc position, and now I'm an assistant professor at the University of Utah. This paper is all about how do we avoid runtime costs using off-the-shelf tools. In this case, the costs come from gradual types, and the tools that we're using are good old statistical profilers. So I'm really excited about this work because it tackles a question that I've had for a long time. So back in POPL 2016, we studied the performance of gradual type systems, and we learned two things. First, that big slowdowns are very common. 10x is on the low end of the slowdowns that we were seeing. And these were all over the place in terms of the possibilities that gradual typing allows you. Many of these possibilities are too slow to run in practice. But we also know that some good points exist, and these are spread throughout, we'll see an example of this, spread throughout the lattice of gradual programs that you can write. So we know these points are out there. How on earth do we find them? And we had some ideas, but we had no way of running the experiment and testing this until recently. And that's this idea of the rational programmer that made this all possible. So gradual types, where do these costs come from? First, here's some untyped code. I've got an untyped function that computes an average of the grades column of a big grading workbook. On the right, I've got a few calls to the average function. Since this is an untyped language, we can call the function with any arguments that we want. So the first call has a check mark because that's a good call. We're passing in an actual gradebook. And the second two are bad calls. And we can run these and see what happens in the untyped code. With gradual typing, we can change just the one average function. We can give that a type annotation and leave all the other code exactly the same as it was before. So this is a well-typed, gradually typed program. If we were to run this program, we would see 2 runtime errors when we do those 2 bad calls to average, but we don't see those until we run. So static time, we only check the types in the yellow part of the code. To do this and have sound types, we're going to need runtime checks, and that's where the costs come from. How much do these checks cost? Well, it depends on the semantics of your gradual types. So there's at least 2 ways of doing the semantics. I can get type soundness, one with the guarded semantics, and this will give us what I'll call deep types. So one way of implementing gradual types is to say I'm going to use contracts at the boundaries between my yellow code and my untyped code, and those contracts are going to guarantee the types. Another way of working is the transient semantics. So this gives us what I call shallow types, and shallow types are implemented by rewriting every line of typed code. So whenever typed code does some operation, we have a quick check, quick assertion that makes sure that the shape of the data that we're getting matches the shape that we're expecting right now. So to put this in terms of our gradebook program, if we have the deep semantics for types, we're going to be checking the entire gradebook once that book crosses the boundary. So that's a big traversal of the data if it's a mutable data structure. And if the gradebook happens to be mutable, we're going to need to put that inside of a wrapper. And now every operation on the gradebook later on, that will pay some cost from that wrapper. In the shallow world, we're going to have a quick check that the thing crossing the boundary is a gradebook. And then when we pull numbers out of that book, we're going to have another assertion that makes sure those are actually numbers and not whatever we would have inside the recipe book. So with these 2 different semantics, we could wind up with very different costs. I've got 9x as the big slowdown from deep types, and it might be 1x after all for the shallow types. Great. Now, if we were to keep migrating this program and go to a fully typed version of it, we can no longer do those bad calls to average. Those will be ruled out statically. But when we run the program, we now get 2 different profiles. The deep types have no cost now because we have no more boundaries between typed and untyped code. The shallow types have a slightly higher cost than before because we've added more typed code to the program. So shallow is paying for every line of typed code. Okay, so now, let's see. We can use deep types, we can use shallow types, we can also use both of these in the same program. And this is work I did last year at PLDI. So we have a large space of possibilities. This is that gradually typed lattice. If we started out with 2 components in the program, we now have 9 possibilities. If we go a little bit, nope. And this raises a big question about once we're at a bad point, like that 9x, where do we go to improve it? There's lots of different ways that we could imagine migrating the program. If we have a slightly bigger program with 3 modules, now we've got 27 points. A tiny bit larger with 4 modules, and the picture barely fits on the slide anymore. So we have a huge search space, and we don't know ahead of time what point in this lattice a developer is going to wind up in. We've got someone who's using gradual types. They're going to pick, basically, to us, an at-random point in this lattice of possibilities, and it's our job as the system designers to make sure that the programmer can quickly navigate to a point that has better performance. Adding types by itself is a bit of a bike shed. You're not adding any functionality to your program. So now that you have to debug these types because they're adding slow runtime, that's even worse. So we want to make this as painless as possible, and that's what motivates the use of off-the-shelf tools. Can we use a profiler, treat the program as a black box, and then navigate to slightly better performance? We're working in typed Racket. We have 2 profilers that we can use. First is the good old statistical profiler, and the second is a slight refinement of that called the contract profiler. When we run statistical profiler, we see output like this table. So we have 1 row basically for every function that can appear on a call stack. And statistical attributes cost to those different points, those functions. I've highlighted in blue and in orange the 2 important outputs that we get from statistical profile. So we care about what's the total % of time we spend at each point, and it might also be interesting to see what was the self-time in each point. So these 2 columns, blue and orange, are going to be important in a few slides. contract profile starts with the same data as statistical profile, but it filters out everything that's unrelated to contracts. So now the report that the contract profiler generates is a list of boundaries ordered from what's the most expensive boundary to the least expensive boundary. So this will directly get us what's the cost of these deep gradual types. So contract profiler, there's just one output we care about. What % of the time do we spend doing this contract? Okay, and these two different profilers, we expect them to behave better or worse in the two different semantics for gradual types. So if our slowdown is due to deep types, the contract profiler should be very well suited to figuring out where are those deep costs. The statistical profiler with total and self, that's less suited. It may help and it may not. With shallow types, the contract profiler should be no help at all because shallow types are not using contracts. They just won't show up in the contract profiler. So then we need to turn to the total % and the self % from the regular statistical. And this is where our problems really start, and this is where we stopped back 6 years ago. We didn't know how to proceed because there are many ways that we can migrate the program, and now there's many different inputs that we can use as a programmer to decide what's the expensive part of the code that I need to focus my migration on. The answer now is to run a rational programmer experiment. So the idea here, bring in a human expert to identify what are possible strategies for doing the migration. Let's get as many strategies as make sense and then put them together in a head-to-head competition. Strategy number 1, for this talk I'll call it the deep strategy. Once you've identified a slow boundary, and there's 3 colors here, yellow, blue, orange, because there are 3 ways that we could identify which boundary is slow. Once we've identified that on the left, convert both sides of the boundary to use deep types. The paper goes into a lot more detail about how this deep relates to what a programmer would be thinking. But for now, find the slowest boundary, migrate both sides to deep. We have a similar strategy for shallow. Find the slowest boundary and turn both sides into shallow. So that's another way that you can, another strategy, another algorithm that you could follow for making these modifications. Shallow also has 3 variants because it could be working with one of 3 types of profile input, but I've left off the colors here. And that's because for the next strategy, there was no space for the colors. The type-aware variant puts a priority order on which boundary to look at. So instead of finding the most expensive one, we want what's the most expensive one that does not require any changes to the types. And if there are no such boundaries, then we'll look at migrating untyped code. So number 1, that's if I have a deep, shallow boundary that's expensive, change the semantics so that they're either both deep or both shallow, depending on if we're on the left side or the right side strategy. And then second, if there's none of these deep, shallow boundaries, then take some untyped code and add types to that. And the reason this one makes sense is because adding types is work. So we skip the work if we can. One other strategy we have is looking at the whole program. What % of that whole program is typed? If less than half the program is typed, use shallow types. If more than half is typed, use deep types. And there's a good reason this makes sense, but I'll leave it for after the talk. And then finally, we have 2 other baseline strategies. The null hypothesis strategy says randomly migrate a boundary to randomly use deep or shallow types. And the PLDI-22 strategy is a 1-step strategy. It takes your current program, turns all the typed modules to be deep or all the typed modules to be shallow, and then stops. So this in prior work was a way to get an order of magnitude improvement, and we'll see if it's successful or not in our experiment. Okay, so now finally, here's the setup for the rational programmer experiment. For all starting points and all the lattices, explore a path towards good performance. What is a fast configuration? That's one that runs at least as quickly as the untyped code. So you're doing at least as well as you were when you had no gradual types at all. And when I'm talking about paths, there's 2 criterion that we're going to use for them. A strictly successful path is like the first one on the bottom. Performance could start off very slow, 99x, stay very slow as long as it gets no worse, and then if we finally get to a 1x configuration, that was a strictly successful path. We'll also loosen that to allow a certain number of slowdowns along the way. So if I start at 3x, bump up to 99x by following the profiler, but then eventually get to 1x, that's successful in the 1 loose sense. We collected a very large data set to run the experiment. We started off with 16 benchmark programs that gave us 100,000 gradually typed configurations. It took 1.2 million measurements to collect all the running times and profiling times that we needed, and that produced 5 gigabytes of output. So we could not have done this work without the help of Cloud Lab, which gave us plenty of single-user machines that we could collect reliable numbers on. So thank you, Cloud Lab. And now let's see the results. We're going to use these skyscraper plots so that we can see a strict success and looser successes on the same figure. So our bars will get thinner as we go up, and that'll be looser and looser. But first, we'll focus on strict success. The x-axis here is our different strategies. The y is the % of all scenarios that they succeed on. Here's some example data. This is the kind of thing that we'll see in the full results. Here, every strategy is a failure except for shallow, which always succeeds no matter what profiler you use, and random succeeds half the time. That's the example data. Okay, now real data for strict success. So we see yellow is much higher than anything else. The contract profiler is the most successful out of all of these. The statistical profiler is not helping us reach these 1x configurations. We also see that when we look to statistical, using the total column or using the self column gives us equivalent results. Neither one is much better than the other. The other thing that really stands out is the deep strategies are far better than the shallow strategies. So shallow and type-aware shallow are near 0. And all three deep strategies are close to one another. So choosing to be type-aware and delaying the work does not much affect the overall success. And also choosing to be lattice-aware, that's along similar lines. Randomly changing boundaries is not very successful, and toggling is also rarely successful. So now what if we loosen things? Let's look at one slowdown along the way. Well, things get a tiny bit better, almost 10%. About 2, 3 loose. Again, incremental improvements. N loose says I'll tolerate any number of slowdowns along the path as long as I finally reach a point that's a fast configuration. N loose is a huge win for random. So randomly changing boundaries, you can get lots of degradations, and sometimes it winds up in good places. But the surprising thing is it does not help the others very much, and especially it does not much help our already successful strategies. So the best ones that we have here are not much better by adding looseness. This was a big surprise to us. One more plot to look at. What if we change the goal line? So instead of looking for something that's a 1x slowdown, just as fast as untyped, we look for 3x. And we see that this helps the shallow strategies a bit. So they're able to achieve a 3x goal line, but it does not help the others very much. So if we were already successful at the 1x mark, changing to 3x doesn't make things much more usable. All right, to wrap up, we have two sorts of takeaways, low-level takeaways and high-level. So at the low level, if you're a programmer using gradual typing, the best way to go for using the profiler to navigate type migration is to go with contract profiling and optimistically go towards deep types when you make a change. Second, we found shallow types do not help much as a stepping stone towards 1x performance. I was very surprised by the shallow types thing. I thought for sure, shallow, you can use that to avoid an order of magnitude slowdown and then take a few more steps to get to a fast point. It seems like that's not a recommendation that I can make at this time. And this points towards some ideas for future work. One, can we find a better hybrid strategy that mixes deep and shallow? And then two, what about a shallow-specific profiler? Contract profiling is tailored toward deep types. Statistical profiling is not tailored toward shallow, so maybe we need a better profiler. At the high level, this rational programmer idea is a powerful tool for enabling rigorous experiments. We could not have done this work without the thinking guidelines that rational programmer gave us. And it's been useful in the past for studying error messages as well, and I think this technique has a very bright future in testing other pragmatic questions about programming languages. The end.
Okay, questions? Anyone? And again, please come up to the mic if you have a question.
Hi, thanks for the talk. I was wondering if you had any statistics for loose, like 1 or 2 loose for strict, for 3x. Because in your...
Yep. So we also have looseness for the 3x goal line. So what that would look like on a skyscraper is more thin lines on top of the already thin line.
Okay.
It's not very exciting.
I see. Thanks.
Hello. So would you use this output to kind of say that if you're starting from an untyped language, that adding like the deep typing is better for performance than the shallow typing?
Adding the deep typing is better if your goal is to reach something that's as fast as the untyped code was.
Yep. Okay.
So, but we also know from prior work that deep types can add these huge multiple orders of magnitude overhead. Shallow types don't do that. They tend to stay under 10x. So I really think that you want both. But if you're going towards fast and fast is what you want, go for deep.
Awesome. Thank you.
Okay. While you're setting up, let me ask one last question. I didn't quite follow why your statistical profiler wouldn't expose the time spent in contract checking. Like, why do you need a separate contract profiler? Why isn't the statistical profiler, why can't you just take the data and say, this is how much time we spent in contract checking?
Right. So statistical profiler is getting all the different things that can add to your stack. It's tracing all functions and all contracts. So the contract data is mixed in, and it can be diluted by the amount of time you spent doing actual work inside of a function. So statistical will point you towards this was the slow part of the program, but I don't know if that was slow because of gradual types or slow because I was doing some important computation.
Okay. Okay. We can talk more offline. Okay. Thank you very much. Let's thank the speaker again. Okay, our next talk is going to be by Jacob Laurel. Jacob's going to be telling us about synthesizing precise static analyzers for automatic differentiation. And I did want to mention that Jacob is on the academic job market this year.
Hi, everyone. Can everyone hear me okay? Awesome. All right, so I'm Jacob. I'm a PhD student at UIUC, and this is joint work done in collaboration with Brant Chian, Gagandeep Singh, and my advisor, Sasa Misailovic. So, hopefully by the end of this talk, I can convince you why automatic differentiation needs precise, general, and scalable static analyses, and why this is possible using our techniques. Now, what do I mean by automatic differentiation? Well, it's a programming paradigm for computing derivatives of source code useful in a variety of tasks like optimization, graphics, scientific computing, and of course, machine learning. Now, what does automatic differentiation actually look like up close? Well, imagine I have some code that encodes a differentiable function. In this case, it's just the exponential function. Now, because it's differentiable, I can think about having another piece of code that can compute that derivative for me. Now, these derivatives are just computed using the standard rules of calculus. Here I've highlighted the statement that encodes the chain rule computation. This is exactly what frameworks like PyTorch, JAX, and TensorFlow all do for you so that as the developer, you don't need to worry about remembering your freshman calculus class. So the question we're interested in is, what if we want to statically analyze this code that computes these derivatives? Now, we might do this in order to try to obtain some type of formal guarantees. In fact, formal guarantees might even be helpful for understanding something about the original function which we're differentiating. Now, you may be wondering, why bother doing this? Well, what if I want to know, do the gradients explode in magnitude? Or is a program, such as a neural network, a monotonic function? How sensitive is the program to different inputs? Well, all these questions can be framed as formal properties, but ones which are definable over derivatives. Now, we're going to compute these derivatives using automatic differentiation, of course, and these formal properties will be analyzed using abstract interpretation. It's the combination of these two that is the foundation of our technique, Passado. Now, a brief recap for those that may be unfamiliar. So imagine I have this piece of source code, and here it's a differentiable program because it performs automatic differentiation to compute a derivative. Now, we're used to starting in some concrete input state, executing the program as normal to obtain a concrete output state. But what if instead of starting in a concrete input state, I were to abstract into what's known as an abstract state, which defines an infinite number of possible states. Then I can propagate that through the program using what's known as abstract interpretation to obtain a final abstract state. Now, of course, this requires abstracting things like the exponential function or this multiplication. I can then concretize back, and now I have an infinite set of reachable output states. Noting that in our case, because we're computing derivatives, this is really an infinite set of derivatives. So, for instance, if we can say that they're all greater than 0, we can now establish a formal guarantee, but one that's not just defined over the derivative computation, but over the original program itself, that the original program must have been a monotonic function. Now, we all know the exponential is monotonic, but this same logic applies to more general functions. So the core idea that I'm trying to illustrate is that a property defined over the derivative code can actually be used to prove a property over the original code, which is called the primal. Now, there's 3 simple rules that govern almost all of calculus. They're the chain rule, the product rule, and the quotient rule. The beautiful thing is that these rules work in both forward and reverse mode automatic differentiation. It doesn't matter the order in which you compute the derivatives, you still have to compute the same derivatives either way. And we can even see this by looking at the source code for the chain rule in both the forward and the reverse mode case, likewise for the product rule and the quotient rule. We see that even though the order of the derivatives is computed, order of the derivatives is different, that we still see the same fundamental patterns emerge in both forward and reverse mode. Now, we're going to notice that these patterns are quite nonlinear due to these multiplications and divisions in the quotient rule. So we might think as a first step to try to abstract these primitive operations. Just as I mentioned abstracting the exponential function or the multiplication in the previous example, we might try that here. And then try to compose together those abstractions using something like interval arithmetic for like interval addition, for instance. But the problem is such a naive composition actually loses precision. This is because a lot of abstract domains like intervals, zonotopes, or polyhedra are well known to be imprecise in the face of nonlinear operations. So we don't want to give up yet. So we revisit these patterns, and we ask the following questions. Is the whole worth more than the abstract sum of the parts? Now, what do I mean by this question? Can we have a single abstraction for the whole expression all at once? And this is exactly the core idea of our technique Pesaro, hence our core contribution. So it might help to illustrate this with a small example. Imagine I have this program, and somewhere in the program I have to compute a sigmoid activation function, which is shown on the right. Well, in the derivative computation, which is what automatic differentiation computes, we see this is the computation I have to perform. I have to do the sigmoid x times 1 minus sigmoid x, which is the derivative of the sigmoid function. Now, in our case, we're trying to abstractly interpret this whole expression all at once. Hence, Pesaro abstractly interprets the chain rule. So we might look at this expression, which we're trying to abstractly interpret, this sigmoid of x times 1 minus sigmoid of x times y, and we might note that it's quite nonlinear. We have several multiplications, and the sigmoid itself is a nonlinearity. But by looking at this graph, we see the function looks close to being linear. So what if we were to come up with a linear approximation of it? Now, by itself, the linear approximation is not sound. We can't just replace every operation in our original code with a linear approximation and hope all is well. But what we can do is try to add some formal bounds to this. So if we can obtain these dark orange linear bounds around the linear approximation, then we can make things sound. The trouble is we have to solve for this d here, because this d governs the amount of offset for the bounds. And notice that the bounds are parallel to the plane that linear regression finds. Hence, the shape is actually a zonotope. So the question then becomes, how do we compute this d? And I'll stress that this is the most important question in order to establish the soundness guarantees for our abstract interpreters. Well, this is not so easy because this is actually a challenging non-convex, nonlinear, multivariate constrained optimization problem. But it turns out if we look at the Hessians, or the matrix of all second derivatives, we can actually make this problem a lot more tractable. So the quotient rule, as an example, this is the optimization problem that we have to solve in order to maintain soundness of the abstract interpreter. Now we're going to look at the objective inside that optimization, and we're going to look at the Hessian in particular. And it turns out that the Hessian of this thing, this four-dimensional function, is actually everywhere indefinite. Now this may not seem particularly useful, but it means that all critical points are saddle points, meaning the optimal value is somewhere along this four-dimensional boundary. And it turns out we can actually repeat this argument for all lower dimensional boundaries as well. Hence, the optimal value is actually on the boundary, thus turning a four-dimensional optimization problem into a handful of 1D optimization problems that are much easier to solve. So while this idea is nice mathematically speaking, how well does it work in practice? Well, take, for instance, this simple climate model, where each letter corresponds to a physically meaningful parameter, such as heat capacity or temperature. So the actual code that we're going to analyze is this numerical ODE solver. We can see it's just a for loop and some assignment statements. Hence, we can automatically differentiate through this piece of source code. And this will allow us to do a sensitivity analysis. Hence, we can understand how sensitive the numerical solution of this ODE solver is to the different inputs or parameters. Noting that in our case, because we're doing abstract interpretation of automatic differentiation, we can do this automatic differentiation through the solver abstractly for ranges of values. Hence, we can analyze a range of physically meaningful values for these conditions. So here are the results, and what I'll first point out is that these blue dots represent the value of performing the automatic differentiation for individual points without using abstract interpretation. If one were to just sample points in those intervals that I mentioned and just run the automatic differentiation on just those points, you would get these blue dots. And hence, the goal is to try to tightly enclose these blue dots as tight as possible. Now, with interval arithmetic or zonotope arithmetic, both of which are standard numerical abstract domains, when you apply those abstract domains to automatic differentiation, you get the green and orange bounds. Now, Posato's bounds are those shown in purple, and they're actually the most precise in all cases. We also will mention that the purple bounds of Posato are always strictly greater than 0. So, for instance, we can prove monotonicity. So we generalize this idea into a full evaluation whereby we compare Posato against interval and zonotope autodiff on 4 case studies. And we use the implementations from our previous papers as the baselines. So the next case study was a Lipschitz robustness with respect to adversarial perturbations. So here we take different neural networks, including some convolutional neural networks, which are quite large. And what we want to do is find the smallest k such that it upper bounds the magnitude of the gradient with respect to the amount of perturbation that the adversary can apply, where the adversary can apply any amount of perturbation from 0 all the way up to alpha max. In particular, the perturbation that we're considering is the Hayes perturbation, where they can apply some Hayes effects to an image. And this requires using the forward mode for Posato. So here are the results. And on the x-axis, we have the alpha max, which represents the interval width of the input perturbation that the adversary can apply. Hence, that's our abstract input state. And on the y-axis, we have the bound on the local Lipschitz constant, and lower is better. So we can immediately see that Posato, which is shown in green, is the lowest. Now, one thing that I'll mention is that these y-axes are shown on a logarithmic scale. Hence, Posato is not just slightly more precise, but rather it is orders of magnitude more precise. And when we look at the runtimes, we see an equally interesting story, and that in the first 2 cases, Posato is not too much slower. So for just a slight increase in runtime, you get orders of magnitude more precision in your bounds. Now, in the last case, Posato is actually slightly faster than zonotope abstract interpretation of autodiff. And that's because Posato is also more memory efficient in that it stores less noise symbols overall. I won't get into that, but I'll just mention that due to this memory efficiency of Posato, in some cases for particularly large benchmarks, that's actually what allows us to be faster. So our last evaluation was a monotonicity analysis of a deep neural network. We take the adult data set, which is a popular data set in algorithmic fairness. And there's multiple categorical features, but we're particularly interested in these continuous input features, things like number of years of work experience, among others. And we want to prove monotonicity with respect to these features, because this monotonicity is an interesting notion of fairness that has recently emerged in the literature. And hence, if we can prove monotonicity with respect to these 5 features, that's our goal, and that can be used as a proxy for fairness. So we have to instantiate Passado in the reverse mode in this setting. And what I'll mention is that each input represents an individual. And what we do is we put an L infinity ball of radius epsilon around each individual. Hence, we're not just analyzing the qualities of the classifier on a single person, but rather on an infinite range of possible people. And so we want to prove as much monotonicity as possible. And so in this graph, higher is better. And what I'll mention is that Passado is the highest. The purple curve of Passado is higher than both interval and zonotope abstract interpretation of AutoDiff, again, due to Passado's improved precision in terms of how it's able to precisely synthesize abstractions. And while the runtimes are a little bit more for Passado, I will mention that compared to interval abstract interpretation of AutoDiff, Passado is able to prove about an order of magnitude more problem instances as monotonic. So there's some more stuff in the paper for those that are interested, such as the full soundness proofs, full experimental evaluation, and our code is available for those that are interested. So just to conclude, I'll say that abstract interpretation of automatic differentiation with Passado, it's precise because we can synthesize precise abstractions for the chain rule, the product rule, and the quotient rule. It's general, it's scalable, and there's a lot of problems at this intersection of automatic differentiation and programming languages, and if you're interested in more of these, I'm on the academic job market this year, so feel free to reach out. Thank you.
Questions?
Hi, this is really cool. So there are 2 things I didn't understand. So one is when you find the zonotopes or those approximations that you build, how are you guarantee that they actually are non-trivial, like the curve?
So are you talking about, I can get back to the slide. Are you talking about this slide?
Yeah, I mean, if you have a weird curve like quadratic, then this can become that the approximation is the entire hyperplane.
So we only look at the chain rule and the quotient rule and the product rule. Those are the only patterns for which we abstract a bound for. So in the general case, for like an arbitrary type of numeric computation, there's not a soundness guarantee for those, but for specifically the computational patterns that are found in automatic differentiation, those are what we do guarantee the soundness for, and that we're able to reduce this down to a handful of one-dimensional optimization problems, and I will so these 1D optimization problems, this is sound for the differentiable functions for which we consider in our language. So.
Okay, got it. So the last part, I was surprised to not find that your last slide was going to be that you can also do abstract training using this abstract domain. Like, can you do like the same that they do with zonotopes, where now you have an objective and you want to train for that instead of just verifying? Yeah,
so that's a great question. So in terms of can you use this technique for training, absolutely. You could use this verifier that we have inside of a training loop, and you could try to train like a neural network to have small gradient bounds, if that's the question.
But how do you pick the bounds to do the back propagation at the point?
So I guess through this, because you have to solve an optimization problem, so it may not be like this particular method in terms of like getting our bounds may not be, as easy to automatically different, like in terms of using our solver inside of a training loop, it may not be possible, but in the general case, using something simpler, like say interval arithmetic or regular zonotope abstractions, those probably could be put inside of a training loop. But for this is mainly targeted towards more of a post-training verification stage. So,
thank you.
Any other questions? Okay, let's thank the speaker again. Context debloating approach for object-sensitive pointer analysis.
Hello, everyone. I'm Dongjie, come from the University of New South Wales. In my presentation, I will introduce a new context deep-routing approach for accelerating object-sensitive point analysis. We know programs writing in C, C++, and Java are usually full of pointers and references. And point analysis answers the following two problems. One, what memory locations can a pointer point to? And two, whether two pointers could be aliases. Point analysis is the foundation of many static program analysis, like compiler optimization, code-graph construction, and so on. It has many implementations in many popular frameworks. In our paper, we focus on object-sensitive point analysis. Object sensitivity is an effective technique in improving the precision of Java point analysis. In object sensitivity, the context elements of the context are receiver objects of some methods. Here is an example of the context in object-sensitive point analysis. Here, the K is the maximum number of context elements in a context. Here is an example. In this code snippet, you can see the other method of the hash state is invoked twice in line 3 and line 4. With two different receiver objects, S1 and S2. So the other method has the receiver object of the other method has two different receiver objects. So the context of the other method will be analyzed in two different contexts, S1 and S2. Generally, when we increasing the K, we can improve the precision of the object-sensitive point analysis. But it can also make the point analysis inefficient or even unscalable. As you can see from this figure, the analysis time of a program called the Lu index increases exponentially as the K increases. So the reason is that the context of object-sensitive analysis grows exponentially with K. Suppose this code snippet is analyzed in different contexts, then the other method of the hash state will be analyzed 2n times in 2n different contexts, S1 CI and S2 CI, where the I could be any number in 1 to n. To address this exponential explosion problem, in my previous publication, I proposed a novel technique called context deep routing. Let's briefly review the key idea of context deep routing. In K object sensitivity, the context elements are objects. And in a program, some objects are context dependent and others are context independent. Here is an illustration of whether an object is context dependent or not. Briefly speaking, an object O is context dependent if analyzing it context insensitively in KOBG. It will cause some program variables to lose precision. The key observation behind the context routing is in the real code, most objects are actually context independent. For example, in this code snippet, the object S1 and S2 are created and used locally and are independent of the calling context. So align context combinations on this object only increase analysis time without any precision benefit. So The key idea of the context debugging is inhibit the context combination on context independent elements. Given the fact that the S1 and S2 here are context independent objects, so we can inhibit the context combination shown in the dotted lines. So the context of the other method will decrease from 2n to 2, which will make the point analysis very efficient without any precision loss. But the challenge in context deblotting is how to precisely identify context-dependent and context-independent objects. In our previous publication, we proposed a context-free language-based approach, which is theoretically undecidable. And the eagle approach, which over-approximates the context-free language, will select almost all non-trivial context-independent objects as context-dependent objects, making the technique less efficient in practice. In the prior context deblotting approach called the CONCH, we approximate the context-free language with 3 linear verifiable conditions. Although it is already very efficient, it is field insensitive, which limits further performance improvements. So in this work, we introduced another context deblotting technique called deployed X. Our technique is one limited field sensitive and could significantly improve the performance with negligible precision loss. Our approach identifies context-dependent objects by usage patterns. We believe that the usage patterns of context-dependent objects in the real code are finite. And we have summarized the following 3 patterns. I will introduce these patterns later. And our evaluation shows that the 3 patterns are enough to preserve 99.8% of precision in the real-world programs. From this slide, I'm going to briefly introduce our approach. Here is the overall algorithm of the context deployed X. It consists only 3 steps and is conceptually very simple. In step 1, given a program P, we first collect container objects in the program. And in step 2, for each container objects, we check whether their usage pattern belongs to any predefined usage patterns. If yes, we will select it to be context dependent. And in step 3, we will return all the context-independent objects to the main point analysis for context deblotting. We first give the definition of the context container objects. An object O is a container object. It must have at least one point field F. And there is an incoming value flow that is stored into O.F, and an outgoing value flow that flows to the outside of the object. As you can see from this figure, we have made an approximation here. We only differentiate one field F and do not care about the other field access path that is longer than the field. So the 2 field access paths in the 2 yellow boxes are aliases in our module. Here is an example code. In this code, the hash set object created in the line 1, marked it as S1, is a container object. Because you can say it has a field map defined in line 5, and an incoming value flow in the other method from the parameter P and stored into this dot map. And an outgoing value flow in the iterator method from this dot map to the return variable and flow out of the method. Here are the rules for identifying the container objects. To compute the incoming and outgoing value flows, we have designed two DFAs. As you can see from the red circles, the DFA differentiates a specific field F. Thus, it is one limited field sensitive. From this slide, I briefly introduce the three use patterns. The first pattern is the inner container pattern. Container object is an inner container if it can be accessed by the out container via a field and could be used by the out containers for storing and retrieving data. As you can see from this example, the hash map object created in the line 4 is associated with this out container via this dot map and is used for storing and storing data in the other method and used for retrieving data in the iterator method. Inner containers are context dependent because they need to distinguish the data stored by their different out container objects. The second pattern is factory created containers. They are usually created in a static method and directly returned in the method. Factory created containers are context dependent because they need to differentiate the data coming from the different calling contexts. And the third pattern is called the container wrappers. Container wrappers in the real code are usually iterators and enumerators. They are usually created in an instance method and directly returned. And their contents are usually come from the method where the objects are created. The container wrappers are context dependent because they need to differentiate the wrapper content from the different calling contexts. This slide just shows the rules for identifying the use patterns. Here is the workflow of our DeployX guided care object sensitive point analysis. We first use a context instance point analysis to analyze the program. And with the imprecise points to information, the DeployX will select a set of context-dependent objects based on the three usage patterns. And finally, the context-independent objects are returned to the main point analysis for context deploying. Our approach is built on top of the chilling framework, and the source code and the artifacts are publicly available. Here are this slide shows the benchmarks, settings, and metrics used in our evaluation. The benchmarks are from the two different versions of the couple benchmark, and so they are very representative. Our evaluation finds that averagely in a program, about 26.7% of objects are container objects, and only 7.6% of objects are context dependent. The ratio of context-dependent objects identified by the three patterns are respectively 4.8%, 1.2%, and 1.7%. The objects identified by the inner container pattern and the container wrapper pattern has a small overlap, but not that significant. Our approach could speed up the K object 19.3 times when K equal to 2, and 150 times when K equal to 3. Comparing with the state-of-the-art approach enables K object to run significantly fast and achieve better scalability. In terms of precision, our approach loses less than 0.2% of precision, which is very close to that of Conch, and is more precise than Zipper. In summary, this paper introduced a new context deploying approach, DeployX based on three container usage patterns. It enables K object sensitive analysis to be more efficient than the state-of-the-art while preserving nearly all of the precision. There's still some work to do in the future. First, we plan to investigate the performance issues on extremely large programs such as the Eclipse. And we also want to develop context deployment techniques for other kinds of context sensitivity like cosine sensitivity. That's all for the presentation. Thanks.
Questions?
Okay, this is amazing how much you debloated. Do you think you could use the same technique to debloat in functional programs?
It's only for object-oriented programs.
But you might identify patterns in functional program that match the patterns from the object world.
Because we only designed the approach based on the object sensitivity, and object sensitivity is currently only very efficient for object-oriented programs.
Okay.
Yeah.
Do you think that there are other object patterns that you're missing that might help with debloating Eclipse? Or what's the slowdown in Eclipse?
Basically, the current 3 patterns is very precise to preserve the precision of the Eclipse benchmarks, but there are still about 200 objects that are mistakenly identified as context-dependent objects, but they are actually context-independent. So this set of objects hurts the efficiency of the analysis, so we still could not analyze these objects scalably. Right.
Thanks. Okay, why don't you get it set up? I had one more question.
Okay.
While he's setting up, so sorry. You showed experiments analyzing against Jerry 1.6 and 1.8, I think is what you showed. And Java 21 was released a few weeks ago. So do you have any idea what happens with more recent Java versions? Are there new analysis challenges that we need to be tackling in order to analyze against more recent standard libraries?
We actually plan to extend the tuning framework into the SweetUp framework so that we can support more features in the most recent version of Java programming languages. Yeah, thanks.
Okay, let's thank the speaker again. Okay, and for the final talk of the session, Thomas Haas is going to tell us about their work on static analysis of memory models for SMT encodings.
Yeah, thank you for the introduction. So my name is Thomas Haas, and this is joint work with my colleagues from TU Braunschweig and Huawei. So, yeah, let's start with a typical verification approach. Say you're given some program and you want to verify it against the specification. And maybe you don't even want to verify it, you just want to find bugs. That's good enough for now. So you might employ a bounded model checking engine. And the bounded model checking engine essentially takes the verification problem and translates it to a logical satisfiability problem and then uses some off-the-shelf solving technique. Now, usually a BMC engine is not just an encoder, but it also uses something like a static analysis to either generate encoding in the first place or to generate more efficient encodings. Now, if you want to argue about concurrent programs, this problem gets a lot harder here, because now we actually need to think about how threads communicate in concurrent programs. And the answer to that is typically, well, over shared memory. And now we get memory into the picture. And memory needs what we call a memory model. And now you want to take this memory model also as an input to the verification task. But now this opens up 3 questions. First, what are memory models? Second, how do we analyze these memory models? And lastly, well, how do we encode them? In this talk, I'm going to answer the first 2 questions. The third one is also part of the paper, but I don't have time in this talk for this. Okay, so first of all, what are concurrent program semantics? Now, let's look at this very simple program here. It has 2 threads, the left one and the right one, and it works over shared memory, the variables x and y. And somewhat atypical, the semantics we associate to this program are actually so-called execution graphs instead of what people usually do, these interleaving semantics. So we look at graphs. And these graphs have nodes, which are called events, essentially corresponding to the instructions of the program. And then they have relations that tell you how these events interact with each other, such as how do they communicate. For example, we have the program order, the black edges here, which essentially just mimic the syntactic structure of the program. So, for example, on the first graph, you see the write x1 is program ordered before the read to y, which is just essentially the syntactic structure of the program, right? Then there's a coherence order, which I just explained on an example here. You see let's take the first graph here. Initially, the memory value of x is set to 0, and at some later point in time, this value is overwritten and set to 1. And this is what the coherence order essentially models, the order in which the memory is overwritten. Each memory cell has its own coherence order. That's why x and y here are independent. And lastly, there's this read from order, which just tells you where does the load take its value from. Okay, so it connects the load and the store. Now you might be wondering, if you look at the first execution, is this actually possible? Like, can this happen? You see both threads here read the value 0, but if you then try to come up with an interleaving that leads to this value, this outcome, you will say this is not possible, because one of the threads starts first and sets some memory value to 1, then the other one cannot see this anymore, right? But then you could also say, well, yes, of course, this outcome is surely possible because maybe your compiler reorders the code during compilation, since it thinks these accesses are independent, or the CPU does out-of-order execution and just executes the code in a different order. Now, to model this, we use so-called memory models, or the full name, memory consistency models. And they simply answer the question, given a program, execution, is it consistent with how the memory works, with how say the buffer structure of the memory works, and how the CPU reorders executions and so on. And the idea is simply to look at the shape of these graphs and of these execution graphs and make a judgment based solely on the shape, not on the data in the graphs. And there exists a language to formulate these memory models called the CAT language. Now we need to take a quick look at the CAT language. So the essential idea is to take these relations you already have, we call them base relations, like the program order, the read from, and the coherence, but there can be more. And then simply define new ones using relation algebra. So you can union them up, you can intersect those relations whatsoever. One problem is that you can also introduce recursion, so you can get nasty relations there. And lastly, you can formulate constraints on these relations, such as some relation has to be acyclic. If this constraint is not satisfied, then the execution is invalid with respect to the memory model. It's not consistent with the memory model. That's the idea. To look at an example, here's the sequential consistency model, which amounts to the idea of interleaving instructions. And if we look at the execution graph there, and then simply evaluate the relations, we get to the following happens before relation graph. You don't need to follow why it looks like that, but I mean, it's relation algebra, union, just some unions and compositions, right? Then we can evaluate the axiom, or the constraint, the acyclicity constraint, and it says, well, this cannot happen. So this is invalid. This execution is not allowed to happen, okay? But then if you look at more realistic memory models that incorporate, say, store buffering effects of actual hardware, then you will find out, oh, sorry, there's a little mistake on the slide. I don't know why. So some real models will say, this is perfectly fine with how the memory works. Due to store buffering effects, you can get this strange outcome. Okay, that's the idea of the CAD language. Now Now you combine this semantics with the program, and you just simply cut off all the executions that do not are inconsistent with respect to the memory model. And this is how you get sort of the combined semantics of program plus memory model. Okay, so now we want to do static analysis. And we want to do some very simple static analysis, actually. Given the program and this cat model, we simply want to find lower and upper bounds for all these relations over all possible executions. So you can think of this as an interval abstraction, but on the level of relations instead of like integers, for example. Now, here is a very simple example. Say we have this set of 3 execution graphs. The lower and upper bounds would look like this. For example, for the read-from relation, there's not a single read-from edge that is common among all these graphs, so the lower bound is empty. The upper bound is simply 4 possible edges that you collect from all these graphs together, okay? On the other hand, for coherence and the program order, you will see all these graphs match, so you have an upper bound and lower bound are equal. There's no difference, okay? Of course, you can also do this for these derived relations in the memory model, so you can also find lower and upper bounds for the from, read, and happens before relation. Okay. Now, it looks very simple, this abstract domain, but there's a little trick here. Because if we look at the lower bounds, we might ask the following question. Say we have this program here which has conditional execution, which is typical in all programs, right? You have some conditional branching. And look at the 2 following execution graphs that are potentially in the semantics of the program. You might say, well, the lower bound of the program order relation is this AB edge, because this is the one common among all the graphs, right? But this notion is too strong because most code in programs is conditional. So you will never really find too many edges that are really common among all program executions because they simply execute different code. So what we did is we relativized this notion of lower bound to just say such an edge in the lower bound means this edge is always there under the assumption that given that the events are executed in the first place. So this is, lower bound is sort of relational. It connects the edge variables or these edges to the execution of the events. Okay. So this then also requires us to incorporate some control flow reasoning to work over this domain. Now let's look at abstract computations. So we have our domain, and now we want to compute things. The idea is that the program restricts the base relations, because like a read from X can only read a value from a store to X, but not from a store to Y. So for example, you can exploit alias information. You can exploit alias information to get information about the read-from relation, about the bounds on the read-from relation. And in general, you can incorporate many program analyses to give some restriction on the base relations. And then these restrictions is what we propagate upwards to the derived relations. And interestingly, the derived relations are then also constrained by the memory model constraints. And this is something we can propagate downwards. And this is what we did in our work. To give you an example, there's a very trivial program. It's not even concurrent. So there's no magic. It's arbitrary code. But it has these 6 events, okay? If you unroll the loop 3 times. In the beginning, the upper and lower bounds are trivial. I'm not going to give you the full graph because, I mean, you don't see much. It's the complete graph. But then we take the program information as input, and it tells us the following. The program order is fixed. So we have a lower bound that is precise because the syntax is fixed, so the program order is fixed. But with respect to read from and coherence, we don't know much. So these dashed edges are the upper bound, okay? Everything can be connected with everything else. Now we can propagate this information upwards and get the following happens before graph of possible happens before relationships. Now we can evaluate the acyclicity axiom, and it tells us none of these back edges are actually possible because they would contradict the lower bound we have for the forward edges. So we would get a cycle. So all of them are gone. And now we can propagate this information also upwards again, downwards, sorry, and remove all the backward edges in the original relations. So there cannot be any backward coherences or backward read-from edges. Interestingly, we can now evaluate the program again because the coherence order is actually a total order. It has to order the store somehow. And we just excluded one possibility, so the other one must be true. It is now part of our lower bound. And interestingly, also the second read you have here, because it has only one possible target where it can read from, this one has also to get fixed, so it's a lower bound as well. And you can do this thing again, propagate up and down, and eventually you will have it completely fixed, which is no surprise because this is a single-threaded program, fully deterministic, so there's nothing open in the end. Everything is fixed. In concurrent programs, it's not so. We get actual differences between the lower and the upper bound. Okay, once we have this information, we want to exploit it. But, well, for that, check our paper. But we use it to generate more efficient SMT encodings. So let's come to the evaluation. We've implemented the analysis in our bounded model checker, D'Artagnan, which takes these memory models as an input in addition to the program. And D'Artagnan already has some static analysis because without any static analysis, the problem does not work at all. Like solving it is not going to work. But this older static analysis was not founded on abstract interpretation, so it was ad hoc. It had no lower bounds, and it did not have the idea of propagating information top-down, just bottom-up. And it has two different solving strategies, one which generates a full encoding, and one which does generate an encoding iteratively in a lazy way. Now, to give you sort of the gist of the evaluation, we have evaluated this on verifying logs and log-free data structures under the ARM and RISC memory model, as well as kernel code of the Linux kernel memory model. And if you look at the red boxes, the top box is always the old result of the verification time without our new analysis, and the lowest row is the improvement. So, for example, for ARM, we could verify our test suite in 20 minutes instead of 30 minutes. And on the Linux kernel, in the Linux kernel, we also got an hour faster in the eager encoding. And even the lazy encoding scheme had some profits from the static analysis. Okay, to summarize, we give a new abstract domain for relations. It's admittedly an easy domain, but with a little twist on the lower bounds. And we give an abstract interpretation-based bidirectional analysis in the sense that it propagates information upwards and downwards. And we show how to use it to improve the SMT encodings. Thank you.
Okay, we have time for a couple of questions.
In terms of the evaluation, can you go back a little bit?
Yeah, sure.
Quick question, what are you verifying here? Where is the specification?
Okay, so we used C implementation of logs and log-free data structures, and we compiled them down to ARM and RISC. And for logs, we check if mutual exclusion holds.
Okay.
And for log-free data structures, we essentially check that multiple push and pop operations, say, do not interfere. So if you have multiple threads that are pushing, no node gets lost during the push. Everything comes to the
and how large is the code for some cases?
I mean,
how many lines, let's say?
In lines of code, it's hard to say. I mean, qspinlog is from a Linux kernel, so it has hundreds of lines of code. The other ones, they're quite small, but we used like 4 threads, and so we scaled it in terms of number of threads. In number of memory events that are happening, so store and load operations, it should be around between 100 and 200 load and store operations. Yeah.
Okay, I'll ask a question. I was trying to think about how you would handle loops and recursion, because then you're going to have a cycle just in the control flow. So do you have to do your bounded unrolling and then do the abstract interpretation?
Yes. I mean, sure. So we do this after the unrolling, since we do bounded model checking. But otherwise, you would have to say, maybe I can show it in some. If you had such a graph, you could start to merge nodes together. So if you have a loop, you just have one representative for all the occurrences of this event. So you compact it. But then, well, the bounds will be less accurate, of course.
Right. But this should mean that you never have to do any widening or anything like that because you don't have any cyclic control flow.
No, we always reduce it to some finite setting, I would say, and then so we don't need to do this.
Yeah. Any other questions?
Oh, sorry.
Okay, let's thank the speaker again.
guys are going to tell me when to start, right? Is this a good spot? I could stand wherever you like. I'd like to the side if it's okay.
Okay, welcome everybody to the second session on program analysis. It's my pleasure to have here Sean, who will start the session with his collaborative work on Historia.
So our research is motivated by my AntennaPod, or my podcast playing application AntennaPod. This is an Android application, and we found a particularly interesting issue in it on their tracker, where a stack trace was reported, just posted online. But very frustratingly for the developers of this application, the stack trace only contains one application method, and all the rest of this is code that actually comes with the phone. It's not code that you have access to when you're writing the application or anything else. And then, even more confusingly, the fix for this is in a completely different callback on destroy. And so the main challenge of our research is how can we help the developer and prove that this fix actually fixes this bug. And as we'll see, this particular issue goes very deep and has some non-trivial properties to it. So let's look into what caused this crash in the first place. An Android application is implemented with a series of callbacks that we'll show in red. The crash happens when this particular callback call is invoked in an unexpected state where the UI is no longer visible, i.e. this act variable is null. And so why this crashes and how it's fixed boils down to why can call be invoked while the UI is not visible. And so we have your phone that has the framework, and it has a whole bunch of stuff going on. But in this case, the call is responding to a background task that loads some media. Typically, this is done off of the UI thread, so you don't make the application non-responsive. And importantly to the rest of this talk, we're going to be talking about the sequence of actions between the Android framework and the application. We call these message histories, and they consist of the name of the callback and arguments such as F. So another event invokes a non-create callback. This event is when you start the view that shows all your podcasts. And in particular, this one calls a method on the framework that, as a dual to callbacks, we call these call-ins. And this goes to the framework with to say start the background loading task. And then we get an unexpected event between these two where the system says, I need memory, clean things up. This is this callback on destroy sets the activity to null. And this allows garbage collection and prevents your phone from running out of memory. But unfortunately, this means that this particular message history with on destroy and call causes this crash. So how's the application fixed? We have our single line in on destroy that I mentioned at the beginning there. And this blocks this final call. And importantly, this isn't just blocking all background tasks. It identifies the specific background task that causes the crash and stops that. And so the reasoning about this fix not only is about the ordering, but it's about the shared values between each of these messages. And we want to understand this fix, we need to know that this particular sequence of create, subscribe, destroy, unsubscribe, call is not realizable under the real framework. So why is it challenging to prove this in real life? Well, the framework code itself is not something that's available to a developer or to us as people writing program analysis tools. It's full of reflection, dynamic code loading, native code, and also you have to develop this app against a bunch of different versions of the phone. There's probably as many versions of Android as there are people who have an Android phone in this room. So that's what you're developing against, is not a whole program at this point. So our main overall insight here is that we want to consider what the framework does as non-deterministic and over-approximate as possible. So we initially assumed that callbacks can be invoked in some non-deterministic order with non-deterministic arguments. And then we do the rest of the verification with the goal in mind that we want to prove that this stack trace is no longer possible. And so we look at this assertion and say, can we show that no message history can reach this failure? And so our first contribution is a way of abstracting control flow without the whole program by considering these message histories. And so the next question is, do you need to model the whole framework? And this becomes important with Android because there's tens of thousands of callbacks and hundreds of thousands of methods that could affect the order of these callbacks. And so, like, writing down a model of this whole thing is a Herculean task. Nobody wants to do that. But one of our key insights is that you really don't have to. Well, the one property that we really care about here is that if l.call is invoked, this callback is invoked with some value L, then in the past there exists a S value representing this task such that unsubscribe has not happened on that since it was returned by subscribe. And that listener object was the same as the subscription object. And so this is our second contribution, is a logic that expresses such things, callback control flow temporal logic, that specifies unrealizable framework behavior as needed. And then the next challenge is, can we automate proofs over this? We have our specification of unrealizable framework behavior. We have our message history logic. And we need to somehow figure out what is possible. And this boils down to what we call excludes initial checks, which will make sense in a little bit. But the main challenge here is that first order temporal logics are usually undecidable. And so making this perform well is a major challenge. And so the contribution is this automatic excludes initial check. And we use SMT solvers in a decidable fragment of logic called extended EPR. So first we'll dive into this control flow, this control flow without the whole program using message histories. So how do we abstract message histories? We do a goal-directed analysis starting with an error condition just before the assertion failure. And this OK-hist thing represents all of the message histories that we have specified as realizable, such as a subscribe and then a call with some other messages intermixed. Also, all the prefixes of a realizable message history are also realizable in this context, like the empty message history. And that's the initial starting point of the program. And then we compute the abstract states backwards around the callback, or along the callback control flow. And we have this funny notation with a double arrow here that's an ordered linear implication. And the idea here is that a call is conceptually appended, and if that is a realizable message history, then the message history that you appended it to is realizable. And so this conceptually removes the call from that previous realizable message history, and it allows us to consider these backwards through the program. But importantly, this excludes the initial message history because you can't just have a call in the application. This would correspond to a task finishing that was never started. And so this is how we maintain precision, because a normal analysis here would have to have an alarm. It would have to just say, I don't know, I got to the framework, I don't have this code. And so the overall idea here is that the execution must have begun with the initial empty message history. And proving this excludes initial is how we handle the maintaining precision there. So overall, how does this work? At this point, we continue overall the different callbacks, and the abstract message histories continue to be appended. How this works is very interesting, so I recommend looking into the paper to see the details. But it ends up that these abstract message histories can be merged automatically. And that means we reach a fixed point, or we often reach a fixed point here. And if the whole invariant that we found excludes the initial, or excludes the empty message history, then the assertion must be safe, because we don't have a way to get from the start of the program to the failure. And so next we'll talk about a little bit about how we specify these things. And the main question that we're answering is we have an abstract message history, and we want to say, is this the initial point of the execution in the Android application? And so we say globally, if call has happened, if this message has happened, then in the past, yesterday, for those who are familiar with past LTL, this formula holds. There exists an S value such that unsubscribe has not been called since subscribe. This is the same one I was talking about earlier. And so this history implication models one callback and two call-ins, and it uses a fragment of past LTL that is enough to capture what we care about. But importantly, this allows us to reason about 3 methods rather than 10,000 callbacks and 100,000 call-ins. And most of the behavior of the framework can be soundly ignored. So next, we'll talk about automating decisions about this. And so I've introduced 2 funny-looking arrows here. And what this comes down to is that they combine and cancel each other out, because we say if a call has happened, then this is true, or a call happens in the future. And then the right-hand side of this figure is what we actually have to reason about. And so to make a long story short, we just have to reason about equality of messages and disequality. And this falls into the category of something that SMT solving is very good at, and in particular this extended EPR logic fragment. So finally, let's take a look at the empirical evaluation. So we started by looking at two apps that document their issues and fixes extremely well. Both apps that I use in watch the issue trackers and watch what kinds of things they run into and how they fix them. So we have 5 issues here that we selected based on things that alter the callback order by adding or removing method calls. And first we asked, could an analysis that has no callback order prove the buggy version safe? And for a few of these, we talk about distinguishing, which is proving the buggy ones, or proving the fixed ones safe and alarming on the buggy ones. And so the no order obviously alarms on all the buggy ones, but it also alarms on all the fixed ones, so this isn't terribly interesting. Then we have the approach of trying to model everything up front. And as you can expect, this is also not great. We find more cases where this proves the buggy versions, so it's unsound. And then Historia, our tool, with targeted modeling, we're able to distinguish all of these. And we find that the number of history implications that I showed earlier, we don't have to write that many. And also, it tends to reach that fixed point I was talking about rather quickly. So to extend this experiment, we went on to open source F-Droid App Store and got 47 apps with 2 million lines of code and found error locations. And we found that 43% were proven safe within an hour. Then we took 8 samples and were able to prove 3 of these by refining the callback control flow and found 1 true bug, and then 4 were timeouts. And then finally, we have 3 of these assertions, and we wanted to look a little bit closer at it, at how hard it is to write the model. So we have the total callbacks and total call-ins, and what we find is that over 95% of the framework does not actually need to be modeled in order to prove these properties safe. So thanks everyone, and just a note, I'm on the job market looking for industrial research jobs if anybody is interested. Thanks.
Very much, Sean. Questions? We have time for 1 or 2. So I might have a question. So what was the average length of these history traces that you are considering? Like how long do the it's a verification effort in essence also, right?
Yeah, so we tracked the number of callbacks deep that it had to explore before reaching a fixed point, and that was typically on the order of like 3 to 5 callbacks, so it reaches the fixed point rather quickly. When there's an alarm, we get 6 to 8 callbacks typically. A lot of that's due to the sparse framework modeling that allows it to be that short. And they tend to be very useful counterexamples is what we've found too.
Okay, thank you very much. Yeah?
Thanks for a great talk. Do you think that there's a way to synthesize or extract these specifications somehow from, for example, logs, doing something like model learning, or trying to somehow figure out in what order different things could happen?
Very good insight. That's the paper I'm working on next, and we already have a prototype that is starting to work. So yeah, that's the idea, is that they're relatively simple specifications, and the hope is that program synthesis can help us figure out what is the framework doing without having to go and read many thousands of pages of Android documentation. So yeah, good insight.
So thanks again, Sean. Our next speaker is Ahmed Zaher, who is going to tell us something about control flow.
All right. Hi, everyone. Thanks for coming. Today I'll be presenting our paper, Exploiting the Sparseness of Control Flow and Call Graphs for Efficient and On-Demand Algebraic Program Analysis. This is a joint work with my colleagues at the Hong Kong University of Science and Technology. So the main point of this paper is to provide efficient algorithms. So first I'll give some context on which problem we're trying to solve efficiently, and then I'll highlight some of the main ideas in our algorithms, and then I'll give experiments and conclusion. So let's start. Suppose that you have a program like this that you wish to verify. And by verify here, I mean that you want to compute a value that summarizes the behavior of this program. Well, one step towards that is to abstract away the syntax by means of a control flow graph, where each node roughly corresponds to a line of code. For example, this line, line 2, corresponds to this node. And the edges of this graph, they correspond to the flow of control. So here we have an assignment. It goes directly to the next line, line 3. But here we have a while. We can have possible branching based on whether or not the while condition is true or not. If it's true, we go to line 4. If it's false, we go to line 7. And then we consider a universe of summaries, A, and the values of that universe, they would correspond to summaries of executions in different parts in my program. And then we define a semantic function that maps edges in that graph to a value that summarizes the effect of taking that edge during execution. And we further extend that by defining an algebra over our summaries that has operators for choice, sequencing, and iteration. And using these two things, we can summarize the entirety of a program that has sequencing and has while loops and has if and else. But we're not interested in just summarizing a whole program. We're interested in something more general. So in particular, we're interested in this collection of values. For each pair of program lines, I and j, we're interested in xij, which should stand for a summary of all paths starting at I and ending at j. These values are what we want to compute. Here's the algebraic approach to compute such values. So suppose we want to compute xij. We first generate a regular expression that is over the alphabet. Its alphabet is the edges of my control flow graph, and we want that regular expression to recognize exactly the paths from I to j. For example, here, if we consider nodes 2 and 7 in this graph, this is a regular expression recognizing all paths from 2 to 7. The next step, to actually get the value of xij, we simply interpret this regular expression using our semantic function and algebra. So we simply replace every edge with its semantic meaning, and we take every operator in the regular expression and replace it with the corresponding operator in my algebra. And what are the applications to this? There are a wide variety of problems in numerical invariant generation and predicate abstraction that can be modeled and solved within this algebraic framework. And we consider an on-demand setting where we have a large stream of queries. Each of them is a pair of program points. And for a query ij, it asks simply for the value xij. And our goal is to answer these queries fast. Why do we care about this on-demand setting? Well, one example is that you can think that we have a large code base, and we have many developers debugging this code base, and each of them are sending queries of this form. They're asking to summarize paths from point I to point j. So more precisely, here's our problem. There's an offline input, which is our program, and an algebra and a semantic function, which correspond to the analysis task we wish to perform. And there's an online input, which is a series of queries. Each of them is a pair of program points. And for each query, we want to compute a regular expression recognizing paths from the query's endpoints, and we want to interpret it in the input algebra. And this should explain this part of the title, on-demand algebraic program analysis. We are referring to this problem here. And what we do in our paper is that we give algorithms to solve it efficiently. So our algorithms, they have a pre-processing phase where we pre-compute some of the queries that have certain special form. And when we later receive a query online, we express it as a combination of the pre-computed queries. And our algorithms are efficient in the sense that both the pre-processing and the query time are fast. And if we first consider the intra-procedural case, where this program, it corresponds to only a single function. In this case, we exploit the sparsity of control flow graph. We note that control flow graphs, they are not arbitrarily complex, that they have some nice structures that we can use. And for the interprocedural case, well, we don't handle it directly, but we do give an algorithm if we suppose that each function is summarized and given at the input. And for this case, to maintain efficiency, we additionally exploit the sparsity of call graphs associated with the program. And this is this part of the title. We exploit the sparseness of control flow and call graphs, and we do that to achieve efficient on-demand algebraic program analysis. So I hope now that the title of our paper makes more sense to you. OK, let's get into some of the ideas in our algorithms. Let's consider first the intra-procedural case, where we have the same problem, but now we know that our program is represented by a control flow graph of a single function. Apparently, this is a very standard graph problem, which is that of computing path expressions. And that problem was already figured out by Tarjan back in the 70s. So if we suppose that n is roughly the number of lines in my program, and that each of these algebra operation, it has cos k, then Tarjan's algorithm, it works on reducible flow graphs, which capture almost all control flow graphs. So it is applicable to our problem. And the algorithm, it computes all queries for a fixed starting point in nearly linear time, which is very nice. But this algorithm doesn't work because it doesn't suit our on-demand setting. If we have many queries with many different starting points, then naively repeating this algorithm would give us a quadratic runtime. And in our paper, we present two algorithms. The first one, it exploits the nesting depth of the program. Unfortunately, I won't be able to talk about it, so you can see the paper. And the second algorithm, it exploits tree width, and this one I will talk more about. OK, so what is tree width? Tree width is a parameter that measures for a graph how similar it is to a tree. So if a graph has low tree width, it is more tree-like, and therefore it admits this structure. It admits a tree decomposition of small bags. What do I mean by that? This is a graph on the left. On the right is a tree decomposition of that graph. It is simply a tree, where each node in that tree, we call it a bag. It corresponds to a subset of nodes in the original graph. And when the graph has low tree width, these bags are small. And this has the nice property that it allows us to successively break this bigger graph on the left into smaller graphs. And we are guaranteed that these smaller graphs are connected or glued together using small cuts. So this enables a kind of a divide and conquer algorithm, where we solve the problem on the subgraph, and to measure the answers for the original graph, we exploit the fact that we have small cuts, so we can afford some brute force over these cuts and obtain the answer for the overall graph. OK, how does tree width relate to our problem at all? Well, Thur showed in '98 that control flow graphs have constant tree width. And an implication of that is that we can assume an extra input, which is a tree decomposition of the control flow graph, and that this tree decomposition has small bags. Now let's try to solve this problem. We are getting queries online. We want to answer them. One naive idea would be to pre-compute all possible queries. And of course, this doesn't work because there are quadratically many queries, and that will take too much time and space. Our approach is to only pre-compute special queries that have certain nice form, such that when we get an online query, we can express it in terms of a combination of the special queries that we already pre-computed. And we want the number of special queries to be significantly less than quadratic. Otherwise, it doesn't differ from the naive approach. And of course, we want the total runtime to pre-compute all of the special queries to be small. So to do that, we will exploit our extra input. So suppose that this is our control flow graph, and this is its tree decomposition. This tree decomposition, it has some properties that give us the following lemma. And it says the following: if you consider two nodes, U and V, in the original graph, like those two here, then you can identify, in the tree decomposition, you can identify two bags, BU and BV, like those shown here in bold. such that the path connecting BU to BV, it is a path consisting of bags, and each of these bags forms a cut that separates U from V in the original graph. So this sounds complicated, so let's see an example. If we pick this bag on the path from BU to BV, it would correspond to this cut, and because it's a cut, if we remove it from the graph, U and V are separated. If we pick this other bag, we remove it, we get the same effect. These two nodes are separated. And this gives us means to break down our query. So if we pick any bag on this blue path, we can break a query from U to V, like this. And so this doesn't only give us a way to break our query, it gives us a choice as to where to break our query. And our idea is to make one canonical choice, which is always the least common ancestor of BU and BV. So in this example, we'd always pick this bag and break our query there. So here's an example. If we pick this bag, a query from 11 to 10, it would be expressed like this. And by this choice, our special queries, we can define it to be all pairs of nodes whose corresponding bags in the tree decomposition are kind of in an ancestor-descendant relationship. And this already gives us an algorithm. In the pre-processing phase, we pre-compute all of these special queries. When we get a query UV, we find the two bags, BU and BV. We find their least common ancestor, and we apply this formula. And by design, we are guaranteed that these things, these answers appearing on the right-hand side, they are special queries, and therefore they are already pre-computed. And then we can compute this whole value. And if we analyze this, we find that the number of special queries is n times the height of the tree decomposition. And if the tree decomposition is too long, then this is bad. We can have quadratically many special queries, which is too much. So we overcome this by defining another decomposition called centroid decomposition. We define it over this tree decomposition. So it has some properties. One of them is that it has height log n. And we, instead of choosing the point where we break our query to be the least common ancestor in this tree decomposition, we choose it to be the least common ancestor in this centroid decomposition. So in this example, we would pick this bag, which corresponds to this bag here, which corresponds to this cut. And now we fix our problem. The number of special queries is n log n. And if you look at the paper, you will see how we pre-compute all of these special queries in n log n times k. That was for the intra-procedural algorithm. How do we handle the inter-procedural case? Again, I won't have much time to talk about it, but we simply extend our algorithm by considering another graph, which is the call graph of the program, and we capture the sparsity of that call graph using another graph parameter, which is tree depth. And we actually did some experiments. We performed some standard data flow analyses that can be formulated within the IFDS framework. So we did reachability, uninitialized variable, and null pointer analysis. And in this case, each algebra element is the graph representation of the IFDS framework. And we tested this on programs from the Cabo benchmarks. And here's a comparison of our algorithm versus using Tarjan's algorithm. We basically run Tarjan's algorithm for every query. And our algorithms indicate by squares. Tarjan is by triangles. And this is time in log scale. And clearly, we're doing faster. We did another experiment where we analyzed Boolean programs. And in this case, each algebra element was a state transformer that's represented by a binary decision diagram. And we used Boolean programs that are generated from Windows drivers while doing abstract interpretation. Again, here's a comparison. To conclude, we gave fast algorithms for on-demand algebraic program analysis. For the intra-procedural case, we exploited sparseness of control flow graphs, and we captured it by tree width. In the intra-procedural case, we looked at another graph, the call graph, and we captured its sparsity by tree depth. And we gave experiments showing that our algorithm is faster than using Tarjan's algorithm for every query. And that's all for my talk. Thank you very much.
Thank you, Amit. Any questions?
Thank you for your talk. There is some clarification question. Your algorithm is n.log n.k. Does it independent with the tree width?
No, we assume that the tree width is constant. But the actual dependency on tree width is, I think, in our algorithm, it's cubic.
Okay, thank you. And I'm also curious about if this algorithm can be generalized to maybe answer data log queries or...
I'm not familiar with that, so I don't know.
Okay, thank you.
Thanks.
Thanks for the great talk. I have a question about the on-demand part, query. What's the complexity of the single query?
Oh, the complexity of a single query. Let's go back. Yeah, we simply apply this formula, and it reduces to a number of queries that is proportional to the number of nodes in this path, which is bounded by the tree width. So it's tree width times a cost of an algebra operation.
Oh, so it's not exponential with respect to tree width?
No, it's tree width times k, where k is the cost of an algebra operation.
Okay, thank you.
Thank you, Amit. Our next speaker is Yuan Dao Chai from Hong Kong University also, who will present his work on a cocktail approach to practical call graph construction.
And thank you everyone for joining my talk. I'm really excited to present our latest progress on call graph construction for C code. I'm Yuan Dao Cai, the first author of this work. A call graph describes the calling relations among functions, which is the backbone of most interprocedural control flow analysis. And look at the call graph. There's a call edge from the function main to the function subchest because in the function main, there is a call side at line 5 calling the function subchest. Call graph construction is one of the most fundamental tasks in the software development process, underpinning various kinds of activities such as program understanding, software testing, and program analysis. A simple search using the keyword call graph on Google Scholar produced over 5 million results. And in the past decade, there have been numerous noteworthy efforts. And in recent years, there is a notable shift from the low-level language like C to higher-level language like Java. And in this world, we consider the unsolved problems of call graph construction for C programs. And specifically, existing approach still suffer from precision and efficiency dilemmas. And we will highlight our approach to significantly mitigate these issues. And C programming still powers the world because there are many low-level systems are writing in C codes, such as operating systems. In C programs, an indirect calls use a function pointer to invoke functions. The benefits of using indirect calls is to making compatible, mimicking object-oriented programming, and enabling dynamic behaviors. Using indirect calls is very prevalent in C-based modern software. According to our study on 5 representative applications on GitHub, about 16.6% of functions are invoked in indirect call. Here's an examples. There is a call side at line 6. The call side is called indirect call because it uses the function pointer to invoke the function subchat. And the simple ways to resolve the indirect call target is to use type analysis, which restrict only to functions that match the types or match the types at indirect calls to resolve the corresponding call is. However, type analysis only consider the type compatibility between the functions and the function pointers, overlooking memory operations. As a result, type analysis is efficient but highly imprecise. Despite the progress, existing pointer analysis suffer from a precision efficiency dilemmas to resolve the function pointers. Specifically, a highly precise pointer analysis that is flow-sensitive, context-sensitive, Anderson style is still super expensive. And here's examples. There are two function pointer, P1, FP1 and FP2 refer to function subtract and function add respectively. And the function wrappers is involved under two calling contexts, context 1 and context 2, and there's an indirect call at line 2. First, flow intensity Stingers pointer analysis had very good efficiencies. It can, in our experiment, it can scale up to 1 million lines of code within 10 minutes. However, Stingers pointer analysis is highly imprecise by treating the assignment as the bidirectional value flow. In this example, Stingers pointer analysis will consider the function pointer FP1 can refer to both functions subtract and add. And second, Anderson's pointer analysis can reach higher precisions but reach median efficiencies. In our experiment, it is still very hard to scale up to 1 million lines of code within 12 hours. And in this example, Anderson's pointer analysis still cannot precisely resolve the indirect call at line 2 because it does not infer any calling context informations. And third, flow context sensitive Anderson style pointer analysis can precisely resolve this case. However, it suffers from bad efficiencies. In our experiments, it is still very hard to scale up to 500,000 lines of code within 12 hours. And we know that the key problems of the previous achievement to resolve function pointer is that existing pointer analysis are irrespective of various kinds of function pointer characteristics, rendering them neither imprecise or unnecessarily precise. And in this world, we consider the scenario where many clients require highly precise call graph, such as program slicing, bug finding. The high precision here means that the analysis should be flow context sensitive, Anderson style, and the analysis should have acceptable efficiencies. Specifically, the analysis should be finished within 12 hours. And to decompose the high cost of constructing highly precise call graph, our basic idea is that not all indirect call require highly precise pointer analysis. And therefore, our intuition is to use more efficient flow insensitive pointer analysis to minimize the numbers of indirect call that require expensive pointer analysis computations. And however, there are two key challenges. The first one is to demystify the reason behind the precise resolution of certain indirect calls through flow insensitive pointer analysis. And the second challenge is to determine which indirect calls have been precisely resolved by the flow insensitive pointer analysis. And it is pretty hard because a precise indirect call can refer to multiple call it because of the dynamic natures of the function pointer. And to understand why a function pointer may be precisely resolved by flow insensitive pointer analysis, we propose the notions of stational function pointers. Stational function pointer, although function pointer remain unchanged for reading after being initialized. And the initialization phase may involve multiple writes. And following the previous work, in this work, we assume that an object's initialization phase has finished when its reference is saved in other objects. And here's examples. This is the lifetime of the function pointer P during the program execution. In the initialization phase, P is written twice across different branches with the values of two functions objects. And the branch conditions are related to the external input. And when the reference to P is stored in other objects, it is assumed that its initialization phase has finished. After that, the function pointer P remains unchanged and is used in indirect call, calling one of the functions based on the external input. And the key challenges, the key feature of the stational function pointer is that any read of them equipped to their initial values, which is irrespective of the calling context and control flow leading up to the corresponding indirect calls. And so how programmers write a stational function pointer? We find that stational function pointers are often used as a global variable and struct view. According to our study on five applications, the proportions of stational function pointer is very high, spanning from 72% to 95%. And there are some examples. The first figure illustrates the global global variable that is a function pointer. Get monotonic as is initialized and written in the function's get monotonic unique. After that, the two indirect calls through assessing the variable can only invoke the initially assigned function irrespective of any control flow. And the second figure shows that in the functions across phase, the stationary field across phase is initialized and assigns one of the A initial values based on the external input. Subsequently, in the function activate, the indirect call through the stationary field can only invoke the A initially assigned function regardless of any control flow because of the field never being reassigned. Return to the second challenge. How can we know an indirect call resolved by flow intensity pointer analysis is already precise? We propose the first approach by checking the initial values of different function pointers and using the flow intensity pointer analysis themselves. The approach is lazy, which means that we can identify already precise indirect call through flow intensity pointer analysis even without knowing which function pointer are stationary beforehand. Here is two examples. For the non-stationary function pointer P, flow intensity that ignore the control flow order or statement, we consider that dereferencing P will refer to three functions, including the initial values F1, F2, and a non-initial value F3. And for the stationary function pointer Q, flow intensity pointer analysis will conclude that dereferencing Q only refers to the initial values F4 and F5, since it is never reassigned after the initializations. To sum up, the initial values provide hints to identify the already precise indirect call through stationary function pointer, conclude by the flow intensity pointer analysis. And based on the insights, we proposed the first cocktail workflow that combines multiple pointer analysis to categorize stationary function pointers. We proposed the first principle for determining the precisions and avoiding unnecessary refinements or indirect calls. Specifically, we propose a pre-analysis to capture the initial values of different function pointers. At the call, we compare the computed values with the initial values, and if they are equivalent, it indicates that the indirect call use stationary function pointers and are precise and do not require further refinements. Also, to improve the efficiencies, we also perform dedicated computation in stage 1, stage 2, stage 3, based on the function pointers of interest. And we use examples to illustrate our approach. The function pointer objects O1 and O2 are allocated at line 2, which are then initialized in the function init. Finally, the objects are passed into the function flow, assessed at the indirect call or line 11 under context 1 and context 2. In our approach, we first perform the pre-analysis to capture the initial values of objects O1 and O2, which are F1 and F2. After running the Stingas pointer analysis at the first stage, we can infer that the pointer V refers to objects O1 and O2, which are imprecise without the calling context informations. However, since the values of both objects are the same and equipped to their initial values, it can be concluded that the indirect call at line 11 used stationary function pointer and had been precisely resolved. As a result, the indirect call, even with multiple call it, does not require expensive flow and context-sensitive computations. And in our evaluation, we choose 20 rather popular and large software systems following the previous work as our benchmark. And 4 programs have more than 1 million lines of code. And we also choose the SUPA as the baseline, which is a flow context-sensitive Anderson's pointer analysis, which had difficulty analyzing 1 million lines of code within 12 hours without considering the stationary function pointers. And we assess the effectiveness of COGA construction by assessing the precision and performance. And we measure the average call it size of all indirect calls and the total time cost spent in the analysis. We also investigate the effectiveness of each stage, such as how efficient the pre-analysis is and how many indirect calls can be precisely resolved by the 2-stage flow intensity pointer analysis. And the results show that our approach is highly effective First, the proposed pre-analysis is very lightweight, and our approach only need to pay negligible time cost in the pre-analysis. That is 1.5 minutes per 780,000 lines of code. This is because the pre-analysis only checks the initialization phase of the function pointers. As a result, the pre-analysis can guide the Stingard's pointer analysis in stage 1 and the Anderson's pointer analysis in stage 2 to recognize about 55% and 25% already precise in direct call through stational function pointer respectively. And the two-stage flow-insensitive pointer analysis can effectively distribute the computational workload, accounting for about 16% of the total time cost. These two-stage enable precise resolution or 80% or all indirect cost, eliminating the need for costly computation in stage 3. As a result, our approach can scale to FFmpeg about 1,200 lines of code within 1 hour and 20 GB memory, which is the first time and cannot be reached by the previous work without considering the stational function pointers. And more experiments and the data can be found in our paper. Thank you so much for listening.
Thank you. Thank you for the presentation. Are there any questions? Sean?
Yeah, interesting work for sure. I was curious, so one of the things I've run into when building call graphs is as I go up in the precision in various call graph construction methods, oftentimes I see that there are more methods that are missing from the call graph that should probably be there, and often it's due to like missing code or anything. I was curious if you could use a similar sort of technique to detect when the call graph construction is unsound.
Sorry, can you repeat your question?
Yeah, so something I found when I've used more precise call graph construction is it's more often missing call edges that should be in the application. And so I was wondering if you could use a similar approach where you start with the less precise call graph constructors to detect when there are call edges that should be there that might not be.
You mean in our approach, how can we identify the false negative?
Yeah.
Missed edge, right? Mm-hmm. Yeah, in our experiments, we try to use some dynamic analysis to collect the ground truth because we don't have the ground truth for the real world application. So we try to use dynamic analysis and fuzzings to collect some real call is and compare the results or our experiments to the collected call it. Yes.
Hey, like the talk. So function pointers in C are used for a lot of reasons because C has very limited mechanisms for abstraction. But systems in like say Rust have things like generics and other things that you might use in place of function pointers. And so I'm curious if you have a sense of like, how are these techniques going to be just useful in the context of C, or do you think that they will generalize and still be applicable for systems written in other languages like Rust?
I think the general ideas or my approach can maybe generalize to other language. For examples, I know in Java there are many stational fields which had been argued in some paper, and I think the idea of the stational function pointer maybe can use for constructing call graph for Java, yeah. But how to extend the idea to other language, and I think it is still an open question.
Okay, thanks.
Thank you again. So the next speaker in our session will be Quan Zhang from Tsinghua University, who will present his work together with his collaborators, of course, on building dynamic system called Sandbox with partial order analysis.
Okay, hello everyone. I'm Chen Zhang from Tsinghua University. Today I will be presenting on building dynamic system called Sandbox with partial order analysis. As software systems become increasingly complex, it is inevitable to introduce security vulnerabilities in these programs. Attackers may exploit this vulnerability and further compromise the host operating system. During the attack, attackers rely on some security-sensitive syscalls, such as exif. To mitigate such attack, security researchers start to employ the system's syscall sandbox to isolate programs. Syscall sandbox can restrict the syscalls that a program can invoke according to a customized policy. With an appropriate policy, the system sandbox can permit the necessary syscalls for the program normal execution, while also limiting the necessary syscalls to mitigate the attack. Therefore, numerous recent works perform advanced static analysis to identify the minimal required syscall set for a program. However, many critical syscalls are initially required by a program, so they are also permitted by existing works. For instance, Nginx requires the syscall setuid and exif, which can be used for remote code execution and privilege escalation. Consequently, even with the syscall sandbox, attackers can still exploit the CVE 2016-0746 in Nginx, compromising the operating system. Nevertheless, we notice that a program required syscall set reduces throughout its life cycle. For instance, the figure shows the life cycle of Nginx. During its life cycle, it is found that the need for exif diminishes once the master process begins in the third phase, and the setuid will be invoked for the last time during the initialization of worker process at the fifth phase. If we adopt a dynamic syscall sandbox that can adjust the syscall policy along the program execution, we can reject the syscall exif and the setuid once they become unnecessary. In this case, even attackers can exploit the CVE at the sixth execution phase of Nginx. They cannot damage the operating system with limited available syscalls. Therefore, by dynamically adjusting the syscall sandbox policy according to the program's demand during its execution, we can effectively mitigate the attack. However, formulating a dynamic syscall sandbox policy is hard, as identifying syscall reduction positions where a syscall becomes unnecessary is challenging. Existing work may manually identify one or two transition points or programs' different execution phase to set the policy, such as the beginning of program's initialization. Nevertheless, such manual identification requires expert experience and extensive efforts, making it impractical to analyze a program's entire life cycle. Therefore, in this paper, we introduce Sandbox, a dynamic syscall sandbox that can adjust the syscall policy during the program's execution. First, it employs partial order analysis to automatically identify the syscall reduction positions where syscalls become unnecessary. Then, at these positions, we perform the implementation during the program's compilation. In detail, we leverage Linux syscom and libsyscom to construct the syscall sandbox and adjust the policy. Syscom is a mechanism provided by Linux, allowing a program to set a customized syscall sandbox for itself. It provides a monotonically decreasing information model that allows the program to only make the policy more strict. Moreover, Syscom sets an independent policy for each thread, where a child process or thread must inherit his parent's policy. With Syscom, we perform the implementation at each reduction position of the program, appending a new rule to Syscom to retract the corresponding syscall. As the figure shows, at two positions, we call Syscom add rule interface to retract exif and set UID respectively. After implementation, a syscall enhanced binary is produced. Then, during execution, it will trigger the affirmation code at the proper positions by itself, restricting the exceed and set UID. Hence, the most critical part of sandbox construction is identifying the cyclical reduction positions for which we propose a partial order analyze. A cyclical reduction position is a pair of adjacent instructions. As the figure shows, if the program executes I1 and jumps to I3, then the cyclical exceed will become unnecessary. Therefore, I1, I3 is a cyclical reduction position for the cyclical exceed. To identify the cyclical reduction position, we should locate the position where the required cyclical set reduces. A required cyclical set for instruction II includes all the cyclicals that are invoked by II and II's subsequent instructions, which is calculated through the mapping phi. From I1 to I3, exceed is removed from the required cyclical set. Next, we further convert the problem of resolving required cyclical set to the problem of determining execution order of instructions. Here, we define the successor relation of 4 instructions. If ij successes I, then there should exist at least one execution trace where ij is executed behind I, or ii equals ij. In this case, ij is termed as the successor of ii. If we can establish the partial order of instructions with the successor relation, where each pair of instructions has at most one determined relation, we can easily identify all the cyclical invoked after any instruction, thereby resolving each instruction's required cyclical set. For instance, we resolve the successor relation of I1, I2, and I3 and exceed, finding that the exceed will not be invoked after I3. Therefore, the main intuition of partial order analyze is to establish the partial order relation of instructions. In the workflow, the analyze first builds a candidate graph according to the program's control flow. Then it transfers the candidate graph to the partially ordered graph, on which it establishes the partial order relation of instructions. Next, based on the relation, the analyze resolves the required cyclical set and the reduction positions, finally constructing sandbox with proper instrumentation. Next, I will introduce each step in detail. In the first step, we build a candidate graph whose nodes are candidate set reduced instructions. A candidate set reduced instruction is an instruction after whose execution the required cyclical set may change. We found that such instructions fall into 2 categories. The first category is a system invocation instruction, as a syscall may become unnecessary after its last invocation. It is found that programs typically invoke syscalls through some libraries' high-level interfaces. For example, printf from libc invokes syscall like write and fill text. Therefore, we utilize the Angular to preprocess each library's binary to resolve the syscall invoked by each interface. The second type involves jump instructions. Since after the program jumps to one branch, some syscall on other branches will become unreachable. A program typically contains both intra-procedure and inter-procedure jumps. Intra-procedure jumps are usually caused by statements like if and will. Inter-procedure jumps are typically function calls and returns. Moreover, some programs may invoke indirect calls, for which we utilize SVF to resolve the targets of indirect calls. After collecting all candidate set reduced instructions, we connect them according to the program's control flow. Finally, we obtain the candidate graph, which can over-approximate the possible execution trace of program. Specifically, for any possible execution trace, we can find a corresponding traverse path on the CG. Next, we transfer CG to the partially ordered graph, denoted as PG. The transformation is performed based on the mapping mu, which correlates each set reduced instruction II in CG to a node NA in PG. The mapping is shown as the equation below. First, the analyze utilizes the function is in cluster to conduct critical sniffing, mitigating the precision degradation caused by illusory traces. Since the building of candidate graph does not consider the context of function invocation, it may introduce some illusory traces where over-approximating programs possible execution traces. To address this, we cluster the instructions of a function in which no critical syscalls are invoked, such as the log function shown in the figure. In this way, we can restrict this critical syscall timely, though it may delay the restriction of other syscalls. After analyzing extensive malicious payloads, we summarize the frequently exploited syscalls as critical syscalls. They are usually related to network operation, permission control, and common execution. Then the mapping is performed based on the traverse paths of CG. If two instructions on CG are mutually reachable, then the two instructions will be mapped to the same node of PG. For example, the figure shows a while loop where both two instructions are mapped to the node N4. When all candidate set reduced instructions in CG are mapped to nodes of PG, the edges from CG are transferred to the PG accordingly. Finally, as the figure presents, we obtain the partially ordered graph. In the graph, node log is the cluster node for all instructions of the function log. Two instructions of while loop is mapped to the node N4 in PG. On PG, we can prove that its nodes are partially ordered with the successor relation. It indicates that each two nodes have exactly one successor relation or they have no relation. Oh, sorry. Therefore, as the right part of figure shows, we can easily resolve the required SQL set for nodes of PG. Next, the required SQL set of nodes can be leveraged to over-approximate the required SQL set of instructions. Specifically, we can prove that if instructions I is mapped to the node NA and I is not clustered by critical syscall sniffing, then the required SQL set of instruction II is a subset of the node NA's required SQL set. In this case, we can ensure that the resolved required SQL set of II includes all syscalls that are needed for program's subsequent execution. Then, based on the required SQL set, we further identify the reduction positions where syscalls are determined to be unnecessary. Finally, with these positions, we construct a customized sandbox for the program. In our paper, we prove that the analyze is sound and the sandbox will not interfere with program's normal execution. The evaluation is performed on 7 complex applications. We evaluate all test suites of applications to validate that sandbox does not interfere with their normal execution. Since sandbox permits different syscalls at distinct execution positions, it is important to evaluate sandbox at applications' different positions. Thus, we gather 43 critical vulnerabilities on all applications and identify their exploitation positions, calculating the average results for each application among all its exploitation positions. We also perform the overhead evaluation, where sandbox incurs 5.07% average runtime overhead on 7 applications. In effectiveness evaluation, sandbox rejects 23.50 and 16.86 more syscalls than chestnut and temporal specialization. Meanwhile, it mitigates 15.88% and 8.90 more payloads. When concentrating on the critical syscalls, as the red boxes show, sandbox can restrict many critical syscalls at proper execution positions where existing work can only permit them during the program's whole life cycle. In case study, we show how the number of permitted syscalls varies during the index execution. As the figure shows, during whole life cycle, sandbox adjusts the syscall policy for 13 positions, which is impractical for human identification. Moreover, sandbox rejects many critical syscalls dynamically, such as exave and setuid. Lastly, sandbox properly handles the multiprocessing program without causing crash. In conclusion, we propose sandbox, a dynamic syscall sandbox that restricts programs unnecessary syscalls during its runtime. Then we designed the partially ordered analyze in which is sung to build done box. Finally, we evaluate that done box outperforms existing measures. That's all. Thank you.
Thank you very much for the presentation. Questions?
Rochester. So good work. I think you mentioned this briefly, but I want to ask you again, how do you identify the original system calls? For example, you have in the application, we usually don't call system calls directly, right? We call libraries, especially for C programs, usually from libc. So like you have a fread, then how did you find this fread, fwrite, this kind of, find them by hand or some automatic tool?
We pre-process these libraries. We analyze the libc and other dynamic libraries to identify which syscalls they are used for each interfaces as pre-results and for our analysis. So during the analysis, we locate the invocation of each library interfaces, and we know which syscall are used by this interface. This part of analysis is performed with Angular, static analyze tool.
Okay, so you use Angular to do for the binaries, and you use that to do some binary instrumentation for your policy, right?
No, we will not instrumentation the binary of libraries. We only instrumentation the code of application.
Oh, application. Then okay, you don't do anything for the directly linked binary library.
Yes.
Okay, that's fine. Yeah, that's actually related to my second question. So in original C code, sometimes it's not common, but you can call system calls directly using assembly language. Do you handle this case?
Yes. They usually invoke the C call with some specific code like C call or yes, we handle this special situation that some program may directly invoke this calls. But actually, in this application, we didn't meet that situation.
Okay, we can talk more offline. Thank you.
Okay, thank you.
I would also have a small question. So you presented your work in a context of safety analysis or for exploitation. Would it also enable optimizations in the case of a virtual execution environment?
Excuse me, the virtual execution.
Yeah, so if you run your programs in a virtualization container of some form, so would this also enable some form of optimizations, like reducing the size of the system layer or something like that?
I think this technique can be utilized on these containers or such as virtualization techniques. But each process is specific for a program. So usually those containers or virtual machines are designed for universal programs and not specific for one program. So this analysis is performed for each program. And if you determine that your container is only used for this program, so you can use this to customize a policy for the program.
Thank you. Thanks again for the speaker. And we will conclude our session with a talk by Wuji Ji from Peking University. He will present his work on improving Oracle-guided inductive synthesis by efficient question selection.
Thank you. So, will it work? Oh, sorry. Oh, great. So, hi everyone. My name is Rui and I come from Peking University. So it's my great honor here to present our recent work on accelerating program synthesis. And the title is Improving Oracle-Guided Inductive Synthesis by Efficient Question Selection. So as a start, let us introduce some necessary background on program synthesis. Program synthesis is a problem about automatically generated programs satisfying some user-provided specifications. And in this slide, for simple, I shall focus on a very popular framework named counterexample-guided native synthesis. In this framework, programs are synthesized by interacting between two key components. The first is an example-based synthesizer, and the second is a verifier. The verifier keeps the full specification of the target program, and in each iteration, the synthesizer just generates candidate programs, and this program will be verified by the verifier. If it is incorrect, such as this case, the verifier will select and generate a counterexample to let the synthesizer generate more accurate candidate programs. And if it gets in the correct program, then the synthesis will succeed, and this program will return. And in most cases, when we are talking about designing program synthesizers, the first thing we would like to do is to let our synthesizer as efficient as possible. So to improve the efficiency of program synthesis, there has been a huge number of research efforts in designing efficient program synthesizers. Yeah, so I believe the names of such synthesizers can fulfill this slide, but I just can only list some of them. And however, there is another, not seems known so important in previous studies. There is a component named the verifier. And in the synthesis procedure, this verifier just plays a very important role to select among different counterexamples. So here, a natural question here is that whether we can improve the efficiency of the whole synthesis procedure by selecting different counterexamples. Let us consider a very simple case where there are 3 different programs remaining, where the first program is what we want, and there are 2 different inputs that can form counterexamples. On the first input, 2 programs output the same, and the third are different. And on the second input, all the 3 programs are different from each other. Then, suppose now, if the verifier selects the first input as a counterexample, then some problem will happen. We can find that the synthesizer can still return the second program as a new incorrect candidate program. At this time, it will lead to another iteration and also another invocation of the synthesizer, leading to a great time cost. And in contrast, if the synthesizer can find the second input to form the counterexample, then the target program will become the only choice satisfying all examples, so that the synthesis result must be correct. So therefore, we know that selecting different examples may result in different efficiency of program synthesis. And motivated by this point, in this paper, we aim to select examples that can reduce the number of iterations, which will in turn improve efficiency of program synthesis. And to start, the first question is that, since we can only measure the number of iterations after the whole synthesis procedure finished, how can we know whether an input is good in some intermediate round? We have studied this problem in an existing study on interactive program synthesis. The basic idea is that a good input should lead to different outputs for different programs in the program space. In this way, we can distinguish correct programs from the others based on their output. As a result, a very useful strategy we denote as the mean pair strategy is we can use the number of pairs of programs that output the same to measure the effectiveness of an input. And what we need to do is to select the input that minimize this factor. Recall the previous example that we already know that the first input is not so good and the second input is better. Let us check what will the mean pair strategy say and compare among these 2 inputs. On the first input, there are 5 pairs of programs output the same, 4 output 0 and 1 output 1. And in contrast, for the second input, there are just 3 pairs of input output the same. There are just 3 pairs of programs output the same. So we can see that the mean pair strategy just tells us the same conclusion about which one is better among these 2 inputs, quite smart. However, the problem is that even though this strategy seems quite effective, the problem is that the approach for interactive program synthesis cannot be applied to, for example, accelerated program synthesis. The problem is that in interactive program synthesis, there is a very long user response time because the user needs to think about what to do. So we can use this time to select the best input very carefully. But in the non-interactive setting, because our goal is just to accelerate program synthesis, therefore we must be careful that the time of selecting a better input should be small, and at least it should be smaller than time it saves. In other words, we need we need not only to select better inputs, but also need to ensure that only a small overhead is introduced. So realizing this scalability challenge in this paper, we focus on reducing the overhead of selecting inputs, and meanwhile follows our previous study that use a mean pair strategy to select examples. What is the main challenge? The main challenge here is that the mean pair strategy is so complex that even calculating the objective value for a single input is time-consuming. That is, the number of pairs of programs that output the same. Let us recall the previous example again. We already know on this example there are 5 pairs of programs output the same. But how can we calculate this number of 5? First, we need to evaluate every program in the program space, and second, we need to compare all pairs to count up how many pairs has the same output. But the actual case is that the program space can be extremely large so that we can neither evaluate all programs nor compare all pairs. So how can we address this challenge? So the first thing is that we can use some domain knowledge. One very important domain knowledge about program synthesis is that in a program synthesis task, the space is usually specified by a very small and simple grammar. And also we can assume this grammar is finite because we can always cut off this program space with a large enough depth limit or size limit. So utilizing this structure, we can calculate something very efficiently. That is, if we can calculate a value recursively along with the grammar, then the time complexity will be bounded by the size of the grammar, then it will be very efficient. So now we have some way to efficiently calculate something, and our final goal is to calculate the objective value, that is the number of programs that output the same. So let's just have a try what will happen. To demonstrate this procedure, let us consider a very simple grammar. It just involves 2 non-terminals, and A expand to B plus B, and B expand to some terminals. And also let us consider a very simple input that X is assigned to 0 and Y is assigned to 2. The start case is the lower non-terminal B, which includes only terminating expansions. This case is straightforward because we can just enumerate all terminals and check whether the outputs are the same and just record the answer. And as a result, there are 3 such pairs that output the same. The most important case is that how to combine the recursive results on non-terminal B to the results on non-terminal A. To see this point, let us consider 2 arbitrary programs in the space of non-terminal A. There are 2 different cases. The first case is that the subprograms are very luckily output exactly the same. Then we know that their 4 output must be the same because X must produce the same output from same input. At this time, from the recursive result, we know that there are 9 pairs of such program pairs, so that this case contributes to 9 pairs to the result of non-terminal A. But some problems will occur about the second case, that is, the sub-results are not so exactly the same. At this time, we can find that the behavior actually depends on concrete sub-outputs, which is also dependent on the concrete behavior of the plus operator. We can list some examples that, for example, in some cases it outputs the same, and some cases it outputs differently. It totally depends on what the concrete result is. But please note that what we want to do is to calculate along with the grammar. And at this time, we don't know what the concrete output is, so our calculation simply fail here. Let's make a summary. What struck us is that the behavior of operator X, of operator plus, depends on the concrete sub-output. It is too complex. What can we do? Just throw away it and replace it with some simple thing. So let us estimate it using some very simple operator that when some different inputs are provided into it, it always has a fixed chance of 10% to return the same output. Then let us see what will happen. The first case is the same, so we can just move to the second case. Then at this time, we can say that each pair has exactly 10% chance to output the same. And we know there are maybe it is not directly, but from the size of non-terminal A and the recursive results, we know that there are 72 pairs remaining that belongs to this case. And then it will contribute 7.2 pairs in expectation to the result of non-terminal A. In this way, we can push forward the calculation and thus calculate the number of program pairs that output the same in a very approximate way, but very efficient way. This is just our idea. We just estimate every operator using very simple random events to ensure that the objective value can be calculated efficiently. Our approach can be integrated into a verifier, and each time we want to calculate a counterexample, it will first generate a series of candidate inputs, and then train a model for each candidate input. The model includes parameters for estimating operators. For example, for the previous plus case, we have a parameter equals to 10%. And then the third step, we will calculate the approximate objective value for each input, which is equal to the expected number of program pairs that output the same. And at last, we just return the best. So that's totally our approach. And the next step is the evaluation. So our core idea is our final goal is to accelerate program synthesis. So the most important thing in our evaluation is to check whether this goal is realized. So we just consider 3 different common synthesis domains and several different synthesizers, and compare our approach with the default verifier on all these synthesizers and all corresponding domains. The result turns out that our approach can achieve speedups for all domains and all solvers. Note that this speedup is for free because from the very start to very end, we just treat the example-based synthesizer as a black box. At last, I would like to take some minutes to talk about something about our approximation. So essentially, our key idea is to estimate the output distribution of a program space with some very, very simple random model. So it may seem very counterintuitive that why it works, because all of us know that the behavior of a specific program can be very complex. Our argument is that even though an individual program can be complex, the behavior of the whole program space can be easy and predictable. We can find many related concepts in other domains, such as in psychology, there is a concept named crowd effects. That is, if there are many people in a group sitting together, they tend to lose their individuality, and we can easily predict their behavior. So the program space is just something like a group of programs, and maybe when we want to estimate the overall distribution, it is not so important to care about the accuracy of some specific program. We can also make some simple demonstration. Let us consider a very simple grammar, just include some two inputs and 2 constants and some comma operators. And then let us consider a fixed input and a depth limit. We can plot the output distribution of these programs within the depths into a figure. And we can say if the depth is 0, we can clearly find something that belongs to the concrete behavior of constants and inputs. And as the depth grows to 1, we can also find something like the semantics of plus and semantics of minus. But the point is that when the program space becomes large enough, such as the depth grows to 5, then the distribution turns out to be quite simple. It's just something like a normal distribution. So, and approximate such a distribution will not be difficult. So that is my presentation, and I would like to stop with some simple conclusion. And in this paper, our goal is to accelerate program synthesis by selecting better examples with a very small overhead. To select better examples, we follow one of our previous studies that used min-pair strategy to select examples. And also to reduce the time cost, we estimated the behavior of operators to make everything can be calculated efficiently. This is some example of our approximation. And we implement our approach and evaluate it again on several different domains and with several different synthesizers, and the results show that we can indeed achieve some speed ups. Yeah. That's all. Thank you very much.
Thank you for this very interesting presentation. Are there any questions? From your experience, does it depend on the type of operators that your language is supporting? Like, does the complexity of the base operators that you use for generating the programs, does it influence the quality of the counterexamples?
Yes, of course. The quality of examples will diverse between different domains, and it will just change. And then For example, on the domain of string, and the operator will be, and the input-output behavior will become much more complex. But meanwhile, at this time, if we can find a really good counterexample, we can exclude a very large number of candidate programs. So it just depends on some domain knowledge, and there will indeed some changes.
Okay, thank you. Last chance for a question? If not, then let's thank our speaker again. I guess this concludes the